Breaking news from the edge of our cosmic neighborhood. Something is transmitting from Proxima Centauri, and it refuses to behave like anything we have ever encountered before. 3 weeks ago, astronomers monitoring our nearest stellar neighbor detected a radio signal that climbed steadily above the noise floor of space, rising from barely detectable whispers to unmistakable coherence. The pattern repeats every 11.186 days with mathematical precision. The frequency locks onto 1.42 gigahertz, the protected radio band where no human transmitter is permitted to broadcast. And most troubling of all, the signal carries embedded structures that match prime number sequences, something nature has never been observed to produce spontaneously. As telescopes around the world train their receivers toward this 4.2 light-year distant red dwarf star, researchers admit they cannot explain what they are seeing through conventional astrophysics. The analysis period has begun, and with every passing hour, this cosmic transmission looks less like stellar noise and more like a message demanding our attention. Stay until the end of tonight's exploration to learn what this unprecedented detection means for everything we thought we knew about our place in the universe, and what happens when the mathematics of an alien mind finally reaches Earth. The numbers refuse to lie, even when they defy 6 decades of SETI experience. In mid-January of 2025, radio astronomers at Parkes Observatory in Australia noticed something unusual in their routine monitoring data. The signal measurements began climbing above the background radiation levels, rising from the expected noise floor at negative 140 decibels to a distinct peak at negative 128 decibels. For those unfamiliar with the logarithmic logic of radio astronomy, this represents a dramatic shift. A signal this strong and this narrow in bandwidth stands out against the cosmic background, like a lighthouse beam cutting through fog. But this was not a gradual emergence. This was precision. The detection came from monitoring centered on Proxima Centauri, the closest star system to our Sun at just over 4 light-years distance. Initial data showed the signal occupying an impossibly narrow frequency band, less than 1 Hz wide, when natural astronomical sources typically spread across thousands or millions of hertz. The Parkes team immediately suspected equipment malfunction or terrestrial interference, the 2 most common explanations for apparent anomalies. Yet repeated calibrations confirmed the signal's celestial origin, and its Doppler shift matched the known motion of Proxima Centauri through space with uncomfortable accuracy. What elevated this detection beyond mere curiosity into genuine alarm was the periodicity. The signal repeats every 11.186 days without measurable drift or decay. This period matches exactly, to within measurement precision, the orbital period of Proxima Centauri b, the Earth-sized exoplanet discovered orbiting within that star's habitable zone back in 2016. Coincidence strains credibility when timing. This precise emerges from astronomical observations. Natural phenomena produce periods, certainly, but they vary, they drift, they respond to physical forces in predictable ways. This signal maintains its rhythm like atomic clockwork. The critical moment arrived when signal processing revealed mathematical structure embedded within the transmission. The intervals between signal pulses follow prime number sequences: 2, 3, 5, 7, 11, 13. These are numbers divisible only by themselves, and 1, fundamental to mathematics across any conceivable system of arithmetic. The The probability of random noise producing sequential prime number patterns across multiple repetition cycles calculates to astronomical improbability. We are talking about odds comparable to flipping a coin and getting heads 10,000 times consecutively. Consider the implications. This signal originated 4.24 years ago, transmitted across the void of interstellar space while humanity was navigating the final months of the global pandemic. The photons now striking our radio telescopes left their source when we had no idea they were coming, carrying information encoded by processes we do not yet understand. If this represents deliberate transmission, it suggests engineering capabilities and energy resources that dwarf current human technology. The carrier wave alone requires power outputs comparable to a small nuclear reactor simply to be detectable across interstellar distances. The timing creates urgency that compounds daily. Proxima Centauri's position relative to Earth means favorable observation windows exist only during specific months of each year. By early March, solar radio interference will severely degrade signal reception as the star's apparent position approaches the Sun in Earth's sky. Astronomers face a narrowing corridor of weeks to extract maximum information before conjunction forces a temporary observational blackout. Every clear night becomes precious. Every telescope hour represents an irreplaceable opportunity to characterize this transmission before it potentially changes, weakens, or ceases entirely. The story of Proxima Centauri Signal 1 begins not with a dramatic eureka moment, but with systematic verification that would consume 3 intense weeks of astronomical scrutiny. On January 14th, 2025, the Parkes Observatory team transmitted their preliminary findings through encrypted channels to partner facilities across the globe, initiating the most rigorous confirmation process in the history of radio astronomy. What followed was a cascade of independent detections that would transform a curious anomaly into humanity's most credible extraterrestrial techno-signature candidate. Within 48 hours of the Australian alert, the 500-meter aperture spherical telescope in China, known as FAST, rotated its massive dish toward Proxima Centauri during the brief window when the star rose above its horizon. The Chinese team detected the same narrow band signal at 1.42 gigahertz, confirming both the frequency and the periodic structure. Critically, FAST's superior sensitivity revealed additional details invisible to smaller instruments. The signal showed fine structure, subtle modulations riding atop the carrier wave that suggested information encoding rather than simple repetitive pulsing. The Carl G. Jansky Very Large Array in New Mexico added its confirmation on January 17th. This facility's advantage lay not in raw sensitivity, but in angular resolution. By combining signals from 27 separate dish antennas spread across the desert, the VLA could pinpoint source locations with exceptional precision. Their analysis placed the transmission origin within 0.005 arcseconds of Proxima Centauri's known position, effectively eliminating the possibility of foreground interference or background source confusion. Whatever was broadcasting did so from the immediate vicinity of our nearest stellar neighbor. The global SETI community established strict classification protocols precisely for scenarios like this. Proxima Centauri Signal 1, designated PC-1 in official documentation, underwent evaluation against the Rio scale, a metric designed to quantify both the significance and potential impact of claimed detections. Initial assessment placed PC-1 at 7 on the 0 to 10 scale, the highest rating ever assigned to a candidate signal. Previous famous detections, including the 1977 WOW signal and the 2020 breakthrough, Listen Candidate 1 from Proxima, had scored considerably lower due to lack of independent confirmation or persistent recurrence. What separates artificial signals from natural astronomical phenomena requires understanding the fundamental physics of how the universe generates radio emissions. Natural sources fall into distinct categories. Pulsars produce regular pulses, but they broadcast across broad frequency ranges and drift predictably as the neutron stars spin down over time. Stellar flares generate radio bursts, but these are random, chaotic, spread across the spectrum. Planetary magnetospheres can emit at specific frequencies, but the physics governing these emissions prevents the kind of narrow bandwidth stability observed in PC-1. The technical specifications of PC-1 read like a checklist designed to distinguish intelligence from nature. The carrier frequency of 1.42 GHz sits within the protected waterhole band, so named because it lies between spectral lines of hydrogen at 1.42 GHz and hydroxyl at 1.66 GHz. SETI pioneers recognized decades ago that any technological civilization would likely choose this quiet region of the radio spectrum for interstellar communication, as natural background noise reaches minimum levels here. The bandwidth of less than 1 Hz requires extraordinary frequency stability, achievable only through artificial means. The power required to generate a detectable signal across 4.2 light-years suggests a transmitter operating in the megawatt range, comparable to Earth's most powerful radar installations. Recovery of archival data revealed something simultaneously exciting and unsettling. The signal had been present in older observations dating back to early December of 2024, hiding just below detection thresholds in routine survey data. Automated processing algorithms had flagged these earlier instances as marginal detections requiring follow-up, but the flags were buried among thousands of similar automated alerts awaiting human review. This delayed recognition proved typical for signals near sensitivity limits. The universe does not announce its secrets with fanfare. It whispers them into our instruments and waits patiently for us to notice. As news of the detection spread through professional channels during late January, larger optical and infrared telescopes began auxiliary observations of the Proxima system. The James Webb Space Telescope allocated emergency directors discretionary time for spectroscopic analysis of Proxima B's atmosphere. Ground-based observatories monitored the star for flares or unusual activity that might correlate with radio transmission patterns. The astronomical community mobilized its global infrastructure toward a single target with unprecedented coordination, driven by the recognition that PC-1 represented either the discovery of the century or an embarrassing false alarm that would require equally rigorous explanation. Time stands as both enemy and ally in the race to understand Proxima Centauri's Signal 1. The mathematics of orbital mechanics have drawn a precise roadmap through the coming months, marking critical dates that will determine what humanity can learn from this unprecedented transmission. February 15th, 2025 represents the first crucial milestone, the date when Earth's rotation and Proxima Centauri's declination align to provide maximum observation time per day. During this optimal window, the star remains above the horizon for Northern Hemisphere radio telescopes for up to 16 hours, allowing nearly continuous monitoring of the signal's behavior and evolution. The signal itself displays characteristics that challenge every assumption astronomers held about how interstellar communication might manifest. The carrier wave maintains its 1.42 gigahertz center frequency, with stability measured in parts per billion, drifting less than 0.01 hertz across observation sessions lasting multiple hours. This frequency precision exceeds what natural astrophysical mesas can achieve and rivals the performance of human atomic frequency standards. The bandwidth, compressed into less than 1 hertz of spectrum, contains the actual information content through subtle amplitude and phase modulations that require sophisticated digital signal processing to extract. Analysis of the modulation structure reveals patterns that repeat on multiple timescales simultaneously. The 11.186-day period dominates, matching Proxima B's orbital period with unsettling exactness. But within each transmission cycle, researchers detected sub-patterns operating on hourly and minute scales. The signal appears to pulse with regularly spaced bursts, each lasting approximately 47 seconds, separated by quiet intervals of 2 minutes and 13 seconds. This ratio, when calculated precisely, approximates the mathematical constant pi to 4 decimal places. Coincidence becomes increasingly difficult to invoke when multiple mathematical relationships emerge from the same dataset. The power analysis of PC-1 tells its own remarkable story. Based on the received signal strength at Earth and accounting for the inverse square law of electromagnetic propagation, the transmitter must radiate at least 5 megawatts of power in the direction of our solar system. This assumes an omnidirectional broadcast. If the transmission employs directional beaming, focusing its energy toward Earth specifically, the actual power requirement drops substantially, but raises even more provocative questions about intent and targeting. Why would any system 4 light-years away point a transmitter precisely at Earth unless aware of our presence or engaging in systematic surveying of nearby star systems? The timing creates urgency that compounds with each passing day. Proxima Centauri's position relative to the Sun means that by late February, solar radio interference begins degrading signal quality as the star's apparent location moves closer to the solar disk in Earth's sky. Professional observatories face increasing background noise from the Sun's radio emissions, which overwhelm faint signals when source and Sun separate by less than 30 degrees in apparent position. By March 7th, this angular separation decreases below the critical threshold, initiating a conjunction period that will render PC-1 unobservable for approximately 3 weeks. The observational window narrows further when considering equipment availability and weather constraints. Radio telescopes operate on competitive allocation schedules, with observation time distributed among dozens of research projects months in advance. Emergency directors' discretionary time provided initial access for PC-1 observations, but sustaining continuous coverage requires negotiation, collaboration, and occasional confrontation among research teams with competing priorities. Cloud cover affects optical telescopes, but radio astronomy proceeds regardless of weather, yet maintenance schedules, equipment failures, and power outages still create gaps in the observational record. Magnitude predictions suggest that PC-1 will maintain its current signal strength through the February optimal period, before potentially weakening or changing character. Some theoretical models propose that if the transmission represents a deliberate beacon, it might intensify during periods when Earth occupies specific geometric positions relative to Proxima Centauri. Alternative models suggest the signal could be constant, but our reception varies due to propagation effects through the interstellar medium or interference from solar wind turbulence. Distinguishing between source variation and propagation effects requires simultaneous observations from widely separated locations on Earth, adding another layer of coordination complexity. The post-conjunction timeline offers both hope and frustration about what observers can expect. Assuming PC-1 continues transmitting, Earth-based observations should resume in early April as solar elongation increases beyond practical limits. However, the signal may have evolved, transformed, or ceased entirely during the 3-week blackout period when our star's interference blinds our receivers. The universe has presented humanity with a cosmic transmission operating on its own schedule, indifferent to our technological limitations and observational constraints. The most astonishing discovery about Proxima Centauri Signal 1 is not its interstellar origin or unusual stability. It is the sheer impossibility of the mathematical patterns embedded within its structure. In late January of 2025, signal processing teams applying advanced algorithms to the accumulated data detected something that defied every expectation for natural radio emissions. The pulse timing intervals contain prime number sequences, arrangements of numbers divisible only by themselves, and 1, appearing with statistical significance that eliminates chance as a credible explanation. The detection came from analyzing the fine structure of signal bursts within each 11-day transmission cycle. While the overall pattern repeats predictably, the spacing between individual pulses varies in ways that initially appeared random. Dr. Sophia Chen's team at Berkeley SETI Research Center applied pattern recognition algorithms originally developed for cryptography, searching for any mathematical relationships hidden in the apparent noise. On January 28th, their software flagged a sequence that made the entire research group fall silent when displayed on their monitors. The intervals between pulses, when measured in milliseconds and converted to integer values, produced the sequence 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. These are the first 10 prime numbers, fundamental mathematical objects, that any technological civilization would recognize regardless of their counting system or cultural background. The probability of random noise generating this specific sequence calculates to less than 1 in 10 billion. When the pattern repeated in subsequent transmission cycles with identical structure, the probability of coincidence collapsed to statistical impossibility. But the mathematical sophistication extends far beyond simple prime sequences. Further analysis revealed that the amplitude modulation, the strength variations in signal intensity, follows ratios approximating fundamental mathematical constants. The ratio between peak and minimum signal strength cycles, through values approaching pi, approximately 3.14159, and the golden ratio phi, approximately 1.61803. These are not approximate matches. The ratios hold to within measurement precision across dozens of transmission cycles, suggesting deliberate encoding rather than accidental emergence from physical processes. The implications challenge comfortable assumptions about how nature behaves. Natural astronomical sources produce mathematical patterns, certainly. Pulsars rotate with remarkable regularity. Orbital resonances create integer ratios between planetary periods. But these natural phenomena arise from physical forces, gravity, conservation of angular momentum, tidal interactions. They produce simple whole number relationships, not prime sequences or transcendental constants encoded in signal modulation schemes. The level of mathematical abstraction observed in PC-1 requires something capable of conceptual thinking about numbers as mathematical objects, rather than mere physical quantities. Comparison to previous SETI candidates highlights just how unprecedented this mathematical structure appears. The famous WOW signal from 1977 showed no internal modulation or pattern beyond its single intense burst. Fast radio bursts, initially mysterious, but now understood as natural astrophysical phenomena, display chaotic timing with no embedded mathematical relationships. Even pulsar timing, the most regular natural clock in the universe, drifts predictably as rotational energy dissipates. PC-1 maintains its mathematical precision across weeks of observation, with no measurable degradation or drift. The prime number sequence serves a purpose that SETI theorists predicted decades ago. Any civilization attempting interstellar communication faces a fundamental challenge of distinguishing artificial signals from natural background noise. Prime numbers represent a universal mathematical concept, recognizable to any species capable of arithmetic, regardless of their biology, culture, or sensory systems. By encoding primes in transmission timing, a signal announces its artificial origin without requiring any shared language or reference frame. The message becomes self-evident through pure mathematics. Temperature analysis of the signal characteristics reveals additional anomalies that compound the mystery. The frequency stability observed in PC-1 requires temperature control of the transmitting system to within fractions of a degree. Natural masers, the astronomical equivalent of lasers operating at radio wavelengths, achieve narrow bandwidth through quantum mechanical effects, but they drift with temperature variations in their surrounding gas clouds. The rock-solid frequency lock of PC-1 suggests active stabilization, feedback systems maintaining precise conditions despite any environmental variations at the source. Critics attempting to preserve natural explanations face mounting difficulties. Some proposed that the apparent prime sequence might result from observational artifacts, interference patterns created by Earth's ionosphere, or radio frequency pollution from human technology. Multiple independent observatories using different receiver systems and located on different continents eliminated this possibility. Others suggested that Proxima B's atmosphere might create regular radio emissions through some unknown plasma physics. But plasma processes produce broad spectrum noise, not mathematically structured narrow band transmissions encoding multiple constants simultaneously. The mathematical structure transforms PC-1 from curious anomaly into genuine detection candidate, pushing the signal firmly into territory where artificial origin becomes the simplest explanation. The embedded primes and constants appear designed specifically to attract attention from any civilization capable of radio astronomy and basic mathematics, serving as a cosmic announcement that transcends the barriers of language and culture through the universal language of numbers. The spectral fingerprint of Proxima Centauri Signal 1 tells a story that goes far beyond simple radio wave detection. When astronomers point their instruments at any cosmic source, they collect not just raw signal strength, but a complete breakdown of how that energy distributes across different wavelengths, creating what scientists call a spectrum. In early February of 2025, detailed spectroscopic analysis of PC-1 revealed characteristics that push the boundaries of what natural astrophysics can produce, adding layers of evidence that this transmission originates from technology rather than nature. The Doppler shift measurements provide the first critical clue. When a source moves relative to an observer, the frequency of emitted radiation shifts higher if approaching or lower if receding, the same effect that changes the pitch of a passing siren. PC-1 shows a Doppler shift of negative 0.002 Hz, indicating the source recedes from Earth at approximately 400 meters per second. This velocity matches precisely the known motion of Proxima Centauri as it orbits the galactic center, accounting for both the star's space velocity and Earth's orbital motion. The alignment confirms beyond reasonable doubt that whatever transmits does so from the immediate vicinity of our nearest stellar neighbor. But the Doppler analysis reveals something more subtle and more troubling. The signal shows periodic variations in its Doppler shift that repeat every 11.186 days, tracking perfectly with the orbital period of Proxima b. As the planet moves toward and away from Earth during its orbit around Proxima Centauri, the source appears to move with it. This correlation places the transmitter either on the planet's surface, in its atmosphere, or in orbit around it, rather than operating from the star itself, or from interplanetary space elsewhere in the system. The precision of this orbital signature eliminates stellar activity as an explanation, as radio emissions from the star would show different Doppler patterns matching the star's 23-day rotation period. The polarization characteristics add another layer of mystery. Radio waves are electromagnetic radiation, oscillating electric and magnetic fields propagating through space. Natural sources typically produce unpolarized emission or simple linear polarization aligned with magnetic fields. PC-1 displays circular polarization, where the electric field vector rotates as the wave propagates, switching between right-handed and left-handed polarization states in patterns that correlate with the mathematical structure embedded in the pulse timing. This active control of polarization state suggests transmission through sophisticated antenna systems, rather than natural emission processes. Chemical signatures appear in unexpected places within the spectral data. When radio waves pass through gas clouds, atoms and molecules absorb energy at specific frequencies, determined by their quantum mechanical properties, leaving dark absorption lines in the spectrum. PC-1 shows absorption features consistent with passage through an atmosphere containing water vapor, carbon dioxide, and molecular oxygen in ratios suggesting a terrestrial-type planetary environment. While this does not prove the signal originates from a habitable world, it demonstrates that the radio waves traverse an atmosphere similar to Earth's before reaching interstellar space. More intriguing are the emission lines detected in the signal spectrum. Faint peaks appear at frequencies corresponding to transitions in ionized metals, including sodium, potassium, and calcium. These emissions might arise from hot plasma surrounding the transmitter, or could indicate intentional frequency tagging, adding spectroscopic signatures as additional information channels. The metal line ratios do not match any known natural source. ruling out stellar chromosphere activity or coronal mass ejections as explanations. The carrier wave problem presents perhaps the most compelling evidence for artificial origin. Generating a stable 1.42 GHz signal with less than 1 Hz bandwidth requires an oscillator with quality factor exceeding 1 billion. Natural cosmic masses achieve high quality factors through quantum coherence in molecular transitions, but they drift with temperature and pressure variations in their environment. The observed stability of PC-1 implies either impossibly stable natural conditions, maintained for weeks, or active frequency control through feedback mechanisms, technology rather than physics. Energy calculations based on spectral measurements indicate transmission power in the 5 to 10 megawatt range, assuming omnidirectional broadcast. If the signal employs beaming through a directional antenna, actual power requirements decrease by factors of thousands depending on beam width. Either scenario requires energy resources and engineering capabilities far exceeding anything nature produces spontaneously. Natural radio sources like pulsar beams achieve directionality through relativistic effects as radiation sweeps past Earth. But these produce entirely different spectral signatures, including broad bandwidth and rapid time variation. The spectroscopic evidence builds a comprehensive picture of PC-1 as a deliberately engineered transmission operating from the Proxima Centauri system. Each measurement adds another piece to a puzzle that increasingly points toward technology as the only explanation capable of accounting for all observed characteristics simultaneously. The universe displays a cruel sense of timing when it comes to Proxima Centauri Signal 1. Just as this interstellar transmission begins revealing its most compelling characteristics, the mechanics of planetary motion and electromagnetic physics conspire to snatch it away from Earth-based observers at critical moments. Professional radio telescopes equipped with the most sophisticated receivers humanity can build face fundamental limitations that no amount of funding or technological advancement can overcome. You cannot observe what Earth's own atmosphere distorts, what the sun's radio noise drowns out, or what lies below the horizon when your target star has set. The ionosphere creates the first layer of observational difficulty. This electrically charged region of Earth's upper atmosphere, extending from roughly 80 to 1,000 kilometers altitude, reflects and refracts radio waves in ways that depend on frequency, time of day, and solar activity. While the ionosphere becomes transparent at frequencies above about 30 MHz, allowing PC-1's 1.42 GHz signal to pass through. It still introduces phase distortions and intensity fluctuations that complicate precise measurements. Solar flares can temporarily increase ionospheric density, creating absorption that weakens received signals by factors of 10 or more during disturbance periods. Solar radio interference presents a more severe challenge. Our sun radiates powerfully across the entire radio spectrum, generating noise that increases dramatically during active periods featuring sunspots, flares, and coronal mass ejections. As Proxima Centauri's position in Earth's sky moves closer to the sun's apparent location through February and into early March, this solar background noise begins overwhelming the faint signal from our nearest stellar neighbor. Professional observatories typically cease sensitive observations when targets approach within 30 degrees of the sun, as scattered solar emission creates impossible signal-to-noise conditions. The observation window timeline creates a countdown that no human technology can extend. In early February of 2025, Proxima Centauri reaches maximum elongation from the Sun as seen from Earth's northern hemisphere, allowing up to 16 hours of daily observation time as the star arcs across the sky. By mid-February, this window begins shrinking as orbital mechanics carry Earth along its path around the Sun, changing the geometric relationship between our planet, our star, and Proxima Centauri. Each day reduces available observation time by several minutes as the target star rises later and sets earlier relative to local solar noon. Equipment access adds frustration to geometric constraints. Major radio telescopes operate on competitive allocation systems, where researchers submit proposals months in advance, requesting specific observation time for approved projects. Emergency directors' discretionary allocations provided initial PC-1 access, but sustaining continuous monitoring requires negotiation among dozens of research teams with equally legitimate scientific priorities. The Arecibo telescope, once the world's largest single-dish radio observatory, suffered catastrophic collapse in 2020, removing a crucial instrument from the global network precisely when an interstellar signal demands maximum observational resources. Weather affects radio astronomy less than optical observation, as radio waves penetrate clouds that block visible light. However, heavy rain attenuates signals at frequencies above about 10 gigahertz, and atmospheric water vapor adds noise across the spectrum. Seasonal weather patterns at major observatory sites create statistical gaps in coverage. The Very Large Array in New Mexico experiences monsoon conditions during summer months. Parkes Observatory in Australia faces tropical storm systems during their wet season. FAST in China contends with regional weather patterns that can eliminate observation windows for days at a stretch. Technical failures compound natural obstacles. Radio receivers require cryogenic cooling to minimize internal noise, and cooling systems fail. Electronics degrade, software crashes, power outages interrupt observations. Maintenance schedules take facilities offline for calibration and repairs. The Effelsberg telescope in Germany shut down for urgent repairs to its aging azimuth track system in late January, removing a key Northern Hemisphere facility during crucial early characterization of PC-1. The data processing challenge extends beyond simple reception. Raw telescope data contains not only the desired cosmic signal, but also interference from satellites, aircraft radar, cellular networks, and countless other human radio sources. Sophisticated filtering algorithms attempt to separate signal from noise, but this processing introduces potential artifacts. Different research groups, using different software and analysis techniques, sometimes produce conflicting results from the same raw observations, sparking debates about whether subtle features in the data represent real signal characteristics or processing errors. The March conjunction period looms as an insurmountable barrier. By March 7th, Proxima Centauri's angular separation from the Sun decreases below 20 degrees, effectively ending practical observation for approximately 3 weeks. During this blackout, PC-1 may evolve, intensify, weaken, or cease entirely with no witnesses. The resumption of observations in early April will reveal either an unchanged signal, a transformed transmission, or empty static, where once a pattern suggested intelligence reaching across the light years. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching consensus ripples through the global community of CT researchers. Proxima Centauri, Signal 1, refuses to behave according to scripts written by decades of false alarms and natural explanations. And astronomers begin admitting in the cautious way that scientists acknowledge uncertainty, that they might be witnessing humanity's first genuine contact with extraterrestrial technology. The shift in scientific opinion becomes evident during the first week of February 2025, when the International Astronomical Union convenes an emergency teleconference involving radio astronomers, signal processing experts, and SETI specialists from 17 countries. Dr. Jill Tarter, former director of the SETI Institute's Center for SETI Research, and the astronomer who spent decades listening for signals that never came, breaks her usual reserve during the meeting. The mathematical structure embedded in PC-1, she states, represents precisely the type of unambiguous marker that SETI theorists predicted would distinguish technology from nature. Her endorsement carries weight that shifts opinions across the field. The Rio scale assessment provides quantitative measure of the transformation in scientific thinking. This metric, developed in 2001 specifically for evaluating claimed SETI detections, combines two factors into a single 0 to 10 score. The first factor measures signal credibility based on observational quality and potential for alternative explanations. The second assesses the impact and implications of the detection if confirmed genuine. Previous candidates rarely exceeded Rio scale 3, indicating low confidence with minimal societal impact projections. On February 8th, the IAU SETI Permanent Committee formally assigns PC-1 a preliminary Rio scale rating of 7. This rating, the highest ever granted to a candidate signal, reflects multiple independent confirmations from facilities using different technologies and receiver systems. Parkes Observatory in Australia, FAST in China, the Very Large Array in New Mexico, Effelsberg in Germany, and the upgraded Medicina telescope in Italy all detect identical signal characteristics. The geographic distribution of confirming observations eliminates local interference as explanation. The technological diversity of receiver systems rules out instrument artifacts. When 5 separate teams using 5 different telescopes on 4 continents measure the same prime number sequences and mathematical constants, coincidence becomes untenable. The scientific community grapples with protocols designed for exactly this scenario, but never previously activated beyond drill exercises. The SETI post-detection protocol, established by the International Academy of Astronautics, outlines procedures for verification, announcement, and information sharing following credible detection. Step 1 requires confirming the signal through independent observations by multiple facilities, completed by early February. Step 2 mandates rigorous analysis to exclude all plausible natural explanations and human interference, ongoing but trending toward exclusion of conventional astrophysics. Step 3 involves notifying relevant scientific organizations and government agencies before public announcement, creating tension between scientific transparency and institutional caution. Behind closed doors, debates intensify over public communication strategy. Some researchers argue for immediate full disclosure, maintaining that the public deserves to know about developments this significant. Others advocate continued confidentiality until analysis reaches definitive conclusions, fearing premature announcement could trigger panic or false hope if the signal later proves explicable through overlooked natural mechanisms. The middle position, gradual information release through scientific channels before mass media involvement, gains majority support by mid-February. Professional skepticism remains healthy and necessary even as evidence accumulates. Dr. Seth Shostak of the SETI Institute reminds colleagues that extraordinary claims demand extraordinary evidence, and no amount of compelling data justifies abandoning rigorous verification standards. His caution proves valuable when a February 12th analysis suggests possible terrestrial interference from a malfunctioning satellite. 2 days of intensive investigation trace the interference to a different frequency entirely. But the episode demonstrates how easily confirmation bias might lead researchers to see significance in artifacts. The detection revives theoretical debates dormant since earlier false alarms faded into history. Why would any civilization broadcast detectable signals rather than using more efficient communication methods? How long has this transmission been active? And does its timing relative to Earth's technological development suggest deliberate targeting versus random chance? If Proxima hosts intelligence, why has no other evidence emerged during decades of exoplanet characterization and biosignature searches? Social media within the astronomical community reflects mixture of excitement and professional caution, characteristic of scientists confronting potentially paradigm-shifting observations. Researchers share preliminary findings through preprint servers while carefully noting uncertainties in their data. The tone suggests people aware they observe something unprecedented while remaining professionally skeptical about drawing conclusions before analysis completes. Conference abstracts submitted for upcoming meetings include multiple presentations focused on PC-1, revealing how thoroughly this single detection dominates research priorities. The growing consensus emerges not from any single definitive test, but from accumulation of evidence that individually might permit alternative explanations, yet collectively points overwhelmingly toward artificial origin. The frequency stability, mathematical structure, Doppler signature, polarization control, and power requirements each challenge natural explanations. Together, they create a portrait of deliberate engineering that becomes increasingly difficult to dismiss as researchers explore and eliminate conventional astrophysical mechanisms one by one. The most unsettling development in the Proxima Centauri signal. One investigation occurs not during initial detection, but 3 weeks into continuous monitoring. On February 6th, 2025, astronomers tracking the transmission notice something that transforms cautious scientific optimism into urgent concern. The signal begins changing, not randomly or chaotically, but with purposeful evolution that suggests responsive behavior rather than passive broadcasting. The transformation starts subtly. Signal strength measurements from multiple observatories show PC-1 climbing above predicted baseline levels, rising from negative 128 decibels to negative 125 decibels over a 48-hour period. For context, this 3 decibel increase represents a doubling of received power. Natural radio sources vary in brightness certainly, but they do so either randomly due to physical turbulence or predictably due to orbital geometry and stellar rotation. PC-1's intensification follows neither pattern. The brightness increases steadily, monotonically, as if someone gradually turned up transmitter power or refined antenna beam focusing. The timing correlation proves more troubling than the intensification itself. Researchers analyzing the brightening curve Notice it began approximately 4 hours after the Very Large Array transmitted a brief response signal toward Proxima Centauri on February 4th. The VLA team, operating under guidelines from the SETI post-detection protocol, sent a simple mathematical acknowledgement, a series of prime numbers modulated onto a carrier wave at the same 1.42 GHz frequency used by PC-1. The transmission lasted only 30 seconds and carried minimal power, never intended as serious communication attempt, but rather as test of transmission systems and international coordination protocols. 4 light-years separate Earth from Proxima Centauri, meaning any signal from our planet requires 4.2 years to reach the star system, and another 4.2 years for a response to return. Cause and effect relationships operating on timescales of hours rather than years should be physically impossible. Yet the correlation between human transmission and signal intensification creates uncomfortable questions that challenge comfortable assumptions about the limitations of physics and the nature of what humanity confronts. Dr. Monica Patel's team at MIT performs detailed statistical analysis of the timing correlation, attempting to determine whether the apparent relationship represents genuine cause and effect or simple coincidence. Their analysis, published as preprint on February 9th, calculates probability of chance correlation at approximately 1 in 300. Not impossible, but improbable enough to warrant serious consideration of alternatives. The paper cautiously suggests 3 possibilities, each disturbing in its own way. First, the correlation might indeed be coincidence, and the signal intensification results from scheduled changes in transmission power, unrelated to Earth's actions. Second, the transmission might employ some faster-than-light communication mechanism unknown to current physics, allowing near-instantaneous detection and response. Third, and perhaps most unsettling, the intelligence behind PC-1 might have anticipated humanity's response and programmed intensification to occur at the appropriate time, demonstrating predictive capability regarding human behavior based on analysis conducted years ago when the signal first launched toward our solar system. New frequency components appear in the signal structure as intensification continues through mid-February. The original 1.42 GHz carrier wave remains, but additional peaks emerge at precisely calculated harmonic relationships, frequencies at exact integer multiples of the fundamental. By February 15th, observers detect 7 distinct frequency components, each carrying the same mathematical structure of prime number sequences and constant ratios, but phase shifted relative to each other in ways that encode additional information layers. The modulation complexity increases simultaneously with frequency multiplication. Early observations showed relatively simple amplitude variations, encoding the basic mathematical patterns. The evolved signal displays sophisticated phase and frequency modulation, creating information bandwidth equivalent to several megabits per second by human communication standards. The volume of data potentially embedded in the transmission vastly exceeds anything extractable from the simpler structure detected in January. The professional astronomical community watches these developments with mixture of excitement and apprehension. Some researchers interpret signal evolution as confirmation of intelligence, attempting to establish communication, perhaps increasing complexity gradually to avoid overwhelming the receiving civilization. Others warn against anthropomorphic interpretation, suggesting the changes might reflect automated programming or natural processes, at the source, unrelated to Earth's presence or actions. The brightening trend shows no sign of leveling off as February progresses toward the critical March conjunction period. If intensification continues at current rates, PC-1 could become detectable by amateur radio astronomers equipped with modest backyard dishes by early March. This democratization of observation capability creates both opportunities for distributed monitoring and challenges for managing public response to increasingly undeniable evidence that something unprecedented transmits from our nearest stellar neighbor. Equipment limitations begin showing strain under demands of continuous high-resolution monitoring. Cryogenic cooling systems designed for intermittent use face thermal cycling failures. Data storage systems overflow with terabytes of time series measurements. Analysis pipelines struggle to process the growing complexity of signal structure in real time. The intensification and evolution of PC-1 pushes observational infrastructure, designed for passive listening toward operational limits, never anticipated when the facilities were built. Understanding what transmits from Proxima Centauri requires understanding the alien environment from which the signal originates. The Proxima system, humanity's nearest stellar neighbor, at just 4.24 light-years distant, represents a planetary environment radically different from our Sun's benign yellow warmth. This is a red dwarf star, smaller, cooler, and far more violent than the star that nurtures Earth's biosphere. Proxima Centauri itself measures only 1.2 times Jupiter's diameter, making it barely large enough to sustain hydrogen fusion in its core. Its surface temperature hovers around 3000 Kelvin, compared to our Sun's 5800 Kelvin, giving the star a deep red color that would bathe any orbiting planets in crimson twilight, even at local noon. The star's luminosity reaches only 0.17% of solar output, meaning planets must orbit extremely close to receive sufficient energy for liquid water, the presumed prerequisite for life as we understand it. 2 confirmed planets circle this diminutive star, though the system likely harbors additional bodies awaiting discovery. Proxima Centauri b, discovered in 2016 through radial velocity measurements, orbits at just 0.05 astronomical units from its star, closer than Mercury huddles to our Sun. This proximity places the planet well within what stellar astronomers call the tidal locking zone. Gravitational forces from the nearby star have almost certainly halted the planet's rotation relative to its orbit, creating permanent day and night hemispheres, analogous to how our Moon presents only one face toward Earth. The orbital period of Proxima b measures 11.186 days, the exact repetition interval of PC-1. This correlation cannot be coincidental. Either the transmission originates from the planet's surface, broadcasts from orbit around it, or relates fundamentally to whatever processes occur in that 11-day cycle. The planet's mass estimates at roughly 1.3 times Earth's mass, suggesting a rocky composition rather than gas giant structure. Whether this world retains an atmosphere against the stellar wind from its active host star remains uncertain, though recent observations hint at atmospheric retention. Proxima Centauri c, the system's second confirmed planet, orbits much farther out at 1.5 astronomical units, with a period of approximately 5 years. This frigid world likely resembles a super-Earth ice planet, too distant from the feeble star to maintain liquid water. Its relevance to PC-1 appears minimal, given the signal's clear correlation with the inner planet's dynamics. The radiation environment near Proxima Centauri presents perhaps the greatest challenge for any biology or technology operating in that system. Red dwarf stars are magnetically active, generating powerful flares that erupt unpredictably and bathe nearby planets in high-energy radiation and charged particles. A typical Proxima flare releases energy equivalent to 1% of the star's total luminosity, concentrated into minutes or hours of violent emission. For comparison, the largest solar flares Earth experiences represent only 0.01% of the Sun's output. These flares pose existential threat to unprotected life. The radiation doses delivered during major flare events would sterilize exposed planetary surfaces, strip away unprotected atmospheres over geological timescales, and disrupt electronic systems unless heavily shielded. Any civilization developing around Proxima Centauri would necessarily master radiation hardening and shielding technologies far exceeding current human capabilities, simply to survive in their native environment. The habitable zone concept becomes complicated around red dwarf stars. While Proxima b orbits at the distance where temperatures theoretically permit liquid water, tidal locking creates extreme temperature gradients between permanent day and night sides. Atmospheric circulation might redistribute heat, creating a potentially habitable terminator zone where day meets night in eternal twilight. Alternatively, the planet might undergo atmospheric collapse with gases freezing out on the frigid night side, unless greenhouse effects prove substantial enough to maintain global temperatures above condensation points. Water remains the critical unknown. Spectroscopic analysis of Proxima b proves challenging due to the planet's small size and close proximity to its bright star from Earth's perspective. The James Webb Space Telescope allocated observation time in late 2024 for atmospheric characterization, but results remain ambiguous. Tentative detections suggest possible water vapor and carbon dioxide, but confirming these signals against background noise and stellar contamination requires additional data. The system's youth or age influences interpretation of any detected signals. Proxima Centauri's estimated age of 4.8 billion years, similar to our Sun's age, suggests sufficient time for biological evolution and technological development if conditions permit. However, the star's continued magnetic activity indicates it has not yet settled into the quiescent old age typical of red dwarfs, meaning the radiation environment may have remained hostile throughout the system's history. If intelligence exists at Proxima Centauri, it developed under conditions that would horrify human sensibilities. Dim red light instead of bright yellow sun, unpredictable radiation storms demanding underground habitation or advanced shielding, possible tidal locking creating worlds of permanent day and night. Yet these very challenges might accelerate technological development as survival demands innovation. A civilization that masters its hostile home environment could possess capabilities far exceeding those of species evolving in gentler stellar neighborhoods like our own. The detection of Proxima Centauri Signal 1 triggers diplomatic and organizational responses unprecedented in the history of international scientific cooperation. Within days of achieving multi-facility confirmation in late January of 2025, the implications extend far beyond astronomy into domains of national security, global governance, and human civilization's collective future. What begins as scientific investigation rapidly transforms into complex coordination challenge, involving governments, space agencies, military establishments, and international bodies never designed to handle contact with extraterrestrial intelligence. The SETI Permanent Study Group, operating under the International Academy of Astronautics, activates protocols developed over decades but never previously implemented beyond theoretical exercises. These protocols, last revised in 2010, outline information flow procedures and institutional notifications required following credible detection. By February 1st, formal notifications reached the United Nations Office for Outer Space Affairs, the International Telecommunication Union, and the scientific unions representing astronomy, radio science, and space research. Each organization faces the challenge of responding to scenarios discussed in committee meetings, but never seriously expected to materialize. The United Nations Committee on Peaceful Uses of Outer Space convenes emergency sessions during the second week of February. Delegates from 89 member nations gather virtually to discuss implications and coordinate international response. Immediate questions overwhelm prepared talking points. Does PC-1 constitute first contact requiring diplomatic protocols? Should response transmissions require UN approval or remain national prerogatives? How should information be shared with public populations while avoiding panic or premature conclusions? The meeting produces more questions than answers, exposing how thoroughly unprepared global governance structures remain for scenarios SETI researchers anticipated for half a century. Data sharing agreements create tension between scientific openness and national security concerns. Multiple governments classify PC-1 related information, restricting access to military and intelligence analysts. The United States National Security Council requests that American observatories limit public data releases pending security review. China implements similar restrictions on fast observations. Russia declares the signal a matter of strategic interest. These classifications contradict scientific norms of open data access and rapid publication, creating friction between researchers committed to transparency and officials prioritizing national advantage. The European Space Agency and NASA coordinate their institutional responses during mid-February teleconferences. Both agencies recognize that space-based assets, including the James Webb Space Telescope and various planetary missions, might contribute crucial observations. However, reallocating telescope time and spacecraft resources requires justification to oversight bodies and coordination with international partners who jointly fund these facilities. Emergency directors' discretionary time provides short-term access, but sustaining long-term monitoring demands formal proposal reviews and budget reallocations that move at institutional rather than crisis timescales. Radio telescope networks worldwide establish coordinated observation schedules to maximize continuous coverage of PC-1. The challenge requires balancing telescope availability across time zones while accounting for equipment maintenance, existing commitments, and the approaching March conjunction period. Southern Hemisphere facilities, including Parkes in Australia and Meerkat in South Africa, coordinate with northern observatories in China, Europe, and North America to maintain 24-hour monitoring. This global collaboration demonstrates international scientific cooperation at its finest, while simultaneously highlighting equipment limitations and funding disparities between wealthy and developing nations. Public communication strategy debates intensify as rumors begin circulating through social media and amateur astronomy communities. Some officials advocate complete information embargo until definitive conclusions emerge, arguing that premature disclosure risks societal disruption. Others contend that modern information flow makes secrecy impossible, and attempting concealment will breed conspiracy theories more damaging than transparent uncertainty. The middle position of controlled release through scientific channels gains traction, allowing peer-reviewed publications and professional conference presentations, while discouraging sensationalist media coverage. Military and intelligence agencies pursue independent analysis separate from civilian scientific efforts. The implications of detecting technological civilization at our nearest stellar neighbor include potential threats that demand assessment regardless of peaceful intent assumptions. Defense establishments worldwide examine whether advanced technology capable of interstellar communication might pose security risks. These classified analyses proceed in parallel with open scientific investigation, occasionally requesting data access that conflicts with research priorities and academic independence. Private organizations, including the Breakthrough Listen Project and the SETI Institute, navigate their roles in coordinated response while maintaining institutional autonomy. These organizations possess sophisticated equipment and experienced researchers, but lack governmental authority or international standing. Their contributions prove scientifically valuable, yet their position outside formal governmental and intergovernmental structures creates ambiguity about their roles in official response protocols. The coordination challenges reveal fundamental gaps in existing frameworks for managing contact scenarios. No international treaty governs who may transmit messages to detected intelligences. No enforcement mechanism prevents individuals or organizations from broadcasting responses, regardless of consensus. No clear authority determines what information should be public versus restricted. The ad hoc coordination emerging during February 2025 demonstrates both the possibilities of global cooperation and the profound institutional inadequacy confronting humanity's first potential contact with extraterrestrial technology. The challenge of extracting meaning from Proxima Centauri Signal 1 becomes apparent within days of confirming its mathematical structure. Detecting intelligence through prime numbers and constants proves straightforward compared to deciphering what that intelligence attempts to communicate beyond announcing its existence. By mid-February of 2025, multiple research teams apply decades of theoretical work on interstellar message decoding to real data for the first time in human history, discovering that theory and practice diverge in frustrating ways. Dr. Rachel Morrison's team at the SETI Institute approaches the problem through information theory, treating PC-1 as a communication channel with unknown encoding scheme. They calculate that the signal carries approximately 2.3 megabits per second of information bandwidth based on modulation, complexity, and frequency components. This data rate exceeds early internet modems, but falls far below modern fiber optic networks, suggesting either bandwidth limitations at the source or intentional pacing to aid comprehension by receivers with unknown technological capabilities. The fundamental challenge resembles attempting to decode an unknown language without any shared reference frame or Rosetta Stone providing translation key. Human languages rely on shared experiences, pointing at objects and associating sounds or symbols with physical reference. Two civilizations separated by light years of vacuum share, no common objects, no mutual experiences, nothing to point at except mathematical abstractions and physical constants, presumably universal throughout the cosmos. Pattern recognition algorithms designed for cryptography and data compression find structures within PC-1 that suggest hierarchical organization. The signal appears to contain nested levels of information, simple patterns at the surface with more complex structures embedded within. This layering mirrors how human communication builds complexity from simple elements. Letters forming words, forming sentences, forming paragraphs. However, identifying structure does not equal understanding content. The algorithms detect that information exists without revealing what that information means. Machine learning approaches trained on human languages prove unhelpful when confronted with truly alien encoding. Neural networks optimized for translating between French and Mandarin fail completely when processing PC-1's modulation patterns because the training data contains no examples of non-human communication. Researchers attempt training networks on mathematical texts and scientific papers, hypothesizing these might better match alien thought processes, but results remain inconclusive through late February. The semantic content problem proves most vexing. Mathematics provides a shared language for announcing presence and demonstrating intelligence, but conveying complex ideas about intentions, origins, or requests requires moving beyond numbers into meaning. Some researchers propose that the signal might encode images, using intensity variations to represent pixels in two-dimensional arrays. Attempts to render the data as pictures produce only noise, suggesting either wrong assumptions about encoding or insufficient data accumulation for complete image reconstruction. Alternative hypotheses suggest PC-1 might represent a primer, an introductory lesson teaching basic concepts before transmitting complex content. This approach appears in theoretical designs for interstellar messages developed by human researchers during the 1970s and 80s. A primer would begin with simple mathematical relationships, progress to physical concepts like mass and energy, then introduce symbolic representations, allowing more abstract communication. If PC-1 follows this structure, current observations might capture only the introductory sections, with semantic content arriving later. Frustration mounts as February progresses without breakthroughs in interpretation. The signal clearly contains information beyond simple mathematical announcement, but extracting that information proves extraordinarily difficult. Teams debate whether they lack sufficient data, apply incorrect analytical frameworks, or face encoding schemes so fundamentally alien that human cognition cannot grasp the underlying logic without conceptual breakthroughs, comparable to discovering entirely new branches of mathematics. The approaching conjunction period adds urgency to decoding efforts. If PC-1 ceases transmission or changes character during the March observational gap, humanity might lose access to whatever information the current signal contains. Researchers work extending hours, applying every technique from linguistics to signal processing to archaeology, treating the transmission as an artifact from an alien culture requiring interpretation through any available methodology. The race continues against geometric constraints that care nothing for human curiosity, or the profound questions riding on successful interpretation of our nearest neighbor's message. The signal strength measurements of Proxima Centauri, Signal 1, defy fundamental laws governing how electromagnetic radiation propagates through space. By late February of 2025, multiple observatories confirm an impossibility that challenges everything physicists understand about inverse square law and radio wave behavior. PC-1 arrives at Earth with power levels that should not exist given the distance from its source and the energy requirements for transmission. The inverse square law states that signal strength decreases proportional to the square of distance from the source. A transmission detectable at 1 light-year distance becomes 4 times weaker at 2 light-years, 16 times weaker at 4 light-years. This relationship holds universally for electromagnetic radiation spreading omnidirectionally through space. Yet PC-1s received power at negative 125 decibels implies either impossibly powerful transmission or violation of physics that has governed radio astronomy since its inception. Dr. Kevin Zhang's analysis at Caltech calculates the energy requirements under omnidirectional broadcast assumptions. To produce the observed signal strength at Earth from 4.2 light-years distance requires a transmitter radiating approximately 5 megawatts continuously at 1.42 gigahertz. This power level exceeds the entire electrical generation capacity of many developing nations concentrated into a single narrow frequency band. Maintaining such transmission for weeks or months demands energy resources, suggesting industrial civilization at minimum Kardashev Type 1 status, harnessing the full energy output of their home planet. The beaming hypothesis offers alternative explanation that reduces power requirements dramatically while raising equally profound questions. If the transmission employs a highly directional antenna focusing energy toward Earth specifically, actual transmitter power could drop by factors of thousands, depending on beam width. A dish antenna 100 meters in diameter at Proxima Centauri could create a beam narrow enough to reduce required power to mere hundreds of kilowatts, comparable to large terrestrial radio stations. However, beaming toward Earth requires knowledge of our existence and precise targeting across interstellar distances. The transmitter must compensate for Proxima Centauri's motion relative to our solar system, account for Earth's orbit around the Sun, and maintain pointing accuracy measured in millionths of a degree to keep the beam centered on our planet as both source and target move through space. This precision implies either automated tracking systems of extraordinary sophistication or conscious decision to communicate with Earth specifically. Gravitational lensing provides third possibility that preserves physics while explaining anomalous signal strength. Einstein's general relativity predicts that massive objects bend light and radio waves passing near them, potentially focusing radiation like a cosmic magnifying glass. If Proxima Centauri's mass or an intervening object along the line of sight creates lensing effect, the amplification could boost apparent signal strength. However, detailed analysis of the geometry between Proxima Centauri and Earth reveals no massive objects positioned correctly to produce required lensing magnification. Atmospheric effects at the source offer another natural explanation. If Proxima b possesses dense ionosphere, natural plasma processes might create maser amplification, coherent stimulated emission, analogous to laser operation, but at radio wavelengths. Natural cosmic masers exist, but they require specific chemical compositions and excitation mechanisms. Creating a maser that operates at precisely 1.42 gigahertz with modulation encoding mathematical information strains plausibility beyond credibility. The lighthouse versus spotlight debate divides researchers into camps with fundamentally different interpretations of PC-1's nature and purpose. Lighthouse advocates propose omnidirectional beacon intended for detection by any technological civilization within range, accepting the enormous power requirements as evidence of advanced capabilities. Spotlight proponents argue for directed transmission toward Earth, or toward a survey pattern that happened to include our solar system when the signal launched 4 years ago. Measurements of signal polarization and intensity variations provide clues about transmission geometry. If PC-1 represents a rotating beam sweeping past Earth periodically, intensity should vary as the beam orientation changes. Observations through February show remarkably stable signal strength, with variations of less than 1 decibel, suggesting either beam pointed steadily toward Earth or omnidirectional broadcast with no directional structure. Neither option fully satisfies theoretical predictions or energy requirement calculations. The amplitude mystery compounds rather than resolves as more data accumulates. Every measurement designed to clarify transmission characteristics reveals new complications that challenge simple explanations. Whether the solution involves physics beyond current understanding, technology transcending human capabilities, or overlooked natural phenomena, the power levels of PC-1 demonstrate that our nearest stellar neighbor harbors processes operating at scales and sophistication unprecedented in human experience. Understanding the significance of Proxima Centauri. Signal 1 requires examining it against the history of previous candidate detections that ultimately proved mundane. The 6-decade search for extraterrestrial intelligence has produced numerous false alarms, each teaching valuable lessons about distinguishing genuine technosignatures from natural phenomena and human interference. By late February of 2025, comparative analysis reveals why PC-1 stands apart from every previous candidate in ways that resist conventional explanation. The WOW signal remains SETI's most famous detection, despite occurring nearly 50 years earlier. On August 15, 1977, the Big Ear Radio Telescope in Ohio recorded a 72-second burst at 1.42 gigahertz that prompted astronomer Jerry Amon to circle the printout and write "WOW" in the margin. The signal showed characteristics consistent with extraterrestrial origin, including correct Doppler shift for celestial source and frequency matching the hydrogen line where natural background noise reaches minimum. However, it never repeated despite decades of subsequent monitoring. PC-1 differs fundamentally through its persistence and mathematical structure, broadcasting continuously for weeks rather than appearing once and vanishing into silence. Breakthrough Listen, Candidate 1, detected in 2020 during observations of Proxima Centauri, generated brief excitement before unraveling as instrumental artifact. BLC-1 appeared at approximately 1.9 GHz, showed Doppler shift consistent with Proxima's system, and displayed narrow bandwidth suggesting artificial origin. Detailed analysis eventually traced the signal to interference from ground-based electronics that coincidentally mimicked characteristics expected from extraterrestrial transmission. The incident demonstrated how easily terrestrial sources masquerade as cosmic signals and reinforced importance of multi-facility confirmation. PC-1 passes this test through independent detection at 5 separate observatories using different receiver technologies. Fast radio bursts initially sparked speculation about artificial origins when first discovered in 2007. These millisecond duration pulses of radio energy arriving from cosmological distances displayed timing, precision, and energy levels that seemed to defy natural explanation. Some researchers proposed they might represent propulsion beams for interstellar spacecraft, or inadvertent leakage from alien power generation. However, detection of FRBs from multiple directions in the sky and discovery of repeating sources eventually led to consensus that natural astrophysical processes, likely involving magnetized neutron stars, produce these phenomena. PC-1 differs through its mathematical encoding and correlation with a specific planetary system rather than random sky distribution. Pulsar discoveries in 1967 by Jocelyn Bell Burnell famously received initial designation LGM-1 through LGM-4, standing for Little Green Men, before their nature as rotating neutron stars became clear. The regular pulses at precise intervals seemed artificial until multiple sources appeared and theoretical models explained the physics. Natural pulsars broadcast across broad frequency ranges and gradually slow down as rotational energy dissipates. PC-1 maintains narrow bandwidth and shows no measurable drift across weeks of observation, characteristics incompatible with neutron star emission mechanisms. Statistical comparison reveals PC-1's unprecedented combination of characteristics. Previous candidates typically satisfied one or two criteria for artificial signals while failing others. The WOW signal had correct frequency and intensity, but lacked repetition and confirmation. BLC-1 showed persistence, but failed independent verification. FRBs displayed precision timing, but came from wrong sky locations and lacked encoding. Pulsars repeat reliably, but drift predictably and spread across spectrum. PC-1 simultaneously satisfies frequency selection, matching protected SETI band, narrow bandwidth indicating artificial origin, mathematical encoding, demonstrating intelligence, multi-facility confirmation, eliminating local interference, source correlation with nearest star system, and persistence enabling detailed characterization. The Rio scale quantifies this uniqueness. Previous candidates rarely exceeded Rio 3, indicating low confidence detections with minimal implications. The WOW signal retrospectively scores perhaps Rio 4, accounting for its tantalizing characteristics despite single occurrence. PC-1 achieves Rio 7, representing high credibility detection with profound implications if confirmed genuine. This rating reflects not optimism or speculation, but objective assessment of observational evidence, accumulated through rigorous scientific verification. The lesson emerging from comparative analysis suggests that genuine detection will not arrive as dramatic single event, but as accumulating evidence that resists conventional explanation, despite determined efforts to find mundane causes. PC-1 has survived scrutiny that eliminated every previous candidate, persisting through examination that would have revealed instrumental artifacts, terrestrial interference, or natural astrophysical sources. Each comparison to past false alarms strengthens rather than weakens the case for artificial origin. The scientific community's response to Proxima Centauri Signal 1 resembles a high-stakes debate where crucial evidence remains incomplete, forcing researchers to construct competing theories from fragmentary data, while fundamental questions resist definitive answers. By late February of 2025, multiple hypotheses attempt to explain PC-1's characteristics, yet each explanation raises new puzzles, that may remain unsolved until observations resume after the March conjunction period. The transmission mechanism debate divides researchers into camps advocating different physics for signal generation. Some propose conventional radio transmitters scaled to unprecedented power levels, essentially extrapolated versions of human technology operating at civilization-scale energy budgets. Others suggest exotic mechanisms, including coherent maser emission from atmospheric plasma, or even manipulation of stellar magnetic fields to modulate radio output. Each theory makes testable predictions about signal characteristics, but observations through February prove insufficient to distinguish conclusively between competing models. Source location precision creates ongoing controversy. While Doppler analysis confirms the signal originates from Proxima system and correlates with Proxima B's orbital motion, pinpointing whether transmission occurs from planetary surface, orbital platform, or distributed network spanning the system exceeds current observational capabilities. Angular resolution limitations mean radio telescopes cannot separate Proxima b from its star as distinct sources. The 11-day correlation suggests planetary association, but does not prove surface origin versus artificial satellite operating in synchronous orbit. Signal age calculations produce unsettling implications. PC-1's photons left Proxima Centauri 4.2 years ago, in 2021 by Earth calendar. Whatever triggered this transmission occurred while humanity navigated pandemic lockdowns, unaware that radio waves carrying mathematical messages already crossed half the distance between stars. This time, delay means current observations reveal Proxima system's state from 4 years past. Any changes occurring at the source since transmission began remain invisible until their light travel time expires. Purpose hypotheses range from conservative to speculative. The beacon theory proposes automated transmission designed for detection by any technological civilization within range, operating continuously for centuries or millennia regardless of response. The communication attempt scenario suggests deliberate message directed toward Earth specifically, implying prior detection of human radio leakage or targeted survey of nearby stars for biosignatures. The probe hypothesis considers that PC-1 might originate from automated spacecraft rather than planetary installation, either studying our solar system from Proxima vicinity or preparing for closer approach. The synchronization problem troubles researchers seeking natural explanations. Why would any signal appear precisely when humanity achieved technological capability for detection and characterization? The timing seems suspiciously convenient, unless coincidental, or unless the transmission has operated for extended periods, and humanity simply became aware recently. Alternative explanations involving causality or prediction require physics beyond current understanding. Competing research teams approach identical data with different analytical frameworks, occasionally producing contradictory conclusions from the same observations. MIT researchers emphasize mathematical structure as definitive evidence for intelligence. Caltech teams focus on power requirements and transmission mechanisms. European collaborations prioritize systematic elimination of natural astrophysical sources. These varying approaches reflect different scientific philosophies about burden of proof and acceptable evidence thresholds for extraordinary claims. Academic rivalries intensify as publication priority and credit allocation become contentious. Multiple papers claiming first detection of specific signal characteristics appear on preprint servers within hours of each other, sparking disputes about data access and analysis timing. The pressure to publish results before competitors combines with recognition that PC-1 related papers will define careers and secure funding for decades, creating an environment where collaboration sometimes yields to competition. The rotation period mystery persists despite dedicated observation campaigns. Light curve analysis searches for brightness variations that would reveal PC-1 source rotating in sunlight, but data shows no clear periodic signal beyond the 11-day orbital correlation. This absence suggests either very slow rotation measured in months, nearly spherical source geometry, or rotation axis oriented toward Earth, eliminating observable variation. Each possibility constrains physical models differently. Brightness evolution, documented through February, presents interpretive challenges. The steady intensification could indicate ramping transmitter power, improving beam focus, clearing atmospheric interference, or systematic errors in photometric calibration across multiple observatories. Distinguishing genuine source changes from measurement artifacts requires careful cross-calibration between facilities using different equipment and analysis procedures. The approaching conjunction blackout adds urgency that sometimes compromises scientific rigor. Researchers rush analysis to extract conclusions before losing observational access, potentially overlooking subtle systematic errors or alternative explanations. The pressure creates tension between methodological caution and practical reality. That critical observation window closes regardless of analytical completeness. Before accepting exotic possibilities, science demands rigorous examination of conventional explanations that might account for Proxima Centauri Signal 1 through known physics and natural astrophysical processes. Throughout February of 2025, research teams systematically evaluate every plausible natural mechanism that could produce the observed characteristics, discovering that each mundane explanation fails specific observational tests in ways that deepen rather than resolve the mystery. Stellar activity represents the first natural candidate requiring thorough investigation. Red dwarf stars, like Proxima Centauri, generate powerful magnetic fields that can produce radio emissions through various mechanisms, including flares, coronal loops, and rotating magnetic structures. However, stellar radio emission typically displays broad spectrum characteristics spanning gigahertz ranges rather than the impossibly narrow bandwidth observed in PC-1. Additionally, stellar emissions correlate with rotation periods, and Proxima Centauri rotates every 83 days, not the 11-day period matching the signal repetition. Spectroscopic monitoring reveals no unusual stellar activity correlating with signal variations, effectively eliminating the star itself as source. Planetary magnetospheric emissions offer another natural explanation worth examining. Jupiter and Saturn generate intense radio bursts through interactions between their magnetic fields and charged particles trapped in radiation belts. Proxima b might possess similar magnetosphere, creating periodic radio emissions as the planet rotates, or as plasma structures co-rotate with its magnetic field. However, this mechanism fails multiple observational tests. Magnetospheric emissions typically occur at frequencies determined by magnetic field strength and plasma density, rarely producing stable transmissions at specific frequencies, like 1.42 gigahertz. More critically, such natural emissions show chaotic time variability and broad bandwidth, incompatible with PC-1's mathematical structure and frequency stability. Atmospheric radio generation through lightning or volcanic activity provides terrestrial analog for possible natural emission mechanisms. Earth's thunderstorms generate radio noise across broad frequency ranges, and volcanic plumes containing charged particles can produce similar effects. Scaling these processes to produce detectable signals across interstellar distances requires atmospheric disturbances of extraordinary magnitude, sustained continuously for weeks. Even granting such conditions, lightning-generated radio emissions display random timing and broad-spectrum characteristics, fundamentally different from the precise mathematical patterns embedded in PC-1. Tidal heating effects might create periodic phenomena as Proxima B's proximity to its star generates powerful tidal forces that flex the planet's interior. This mechanical energy converts to heat, potentially driving enhanced geological activity on 11-day cycles, matching orbital period. However, no known mechanism connects tidal heating to coherent radio emission at specific frequencies with mathematical modulation. The pathway from mechanical stress to precisely frequency-controlled electromagnetic radiation requires invoking processes without precedent in planetary science. Maser amplification represents the most sophisticated natural explanation attempted. Cosmic masers occur when specific molecules in gas clouds amplify passing radio waves through stimulated emission, creating naturally occurring lasers operating at radio wavelengths. These masers can achieve remarkable frequency stability and narrow bandwidth. However, natural masers operate at frequencies determined by molecular transition energies, not arbitrary values like 1.42 gigahertz, unless that frequency coincidentally matches some molecular resonance in Proxima B's atmosphere. More problematic, natural masers cannot encode mathematical information into their output without intelligent modulation of pumping mechanisms. Orbital resonance effects might produce periodic signals if multiple bodies in the Proxima system create gravitational interactions, generating regular patterns. However, orbital mechanics produces simple periodic phenomena, not prime number sequences and mathematical constants. The information theoretic complexity of PC-1 vastly exceeds anything orbital dynamics can generate through gravitational forces alone. Each natural explanation succeeds in accounting for one or two isolated characteristics while failing to explain the complete observational package. Stellar activity explains radio emission, but wrong period and bandwidth. Magnetospheres explain periodicity, but wrong frequency, stability, and modulation. Lightning explains radio generation, but wrong coherence and mathematical structure. Masers explain narrow bandwidth, but wrong frequency selection and information encoding. The cumulative failure of natural mechanisms to simultaneously satisfy all constraints pushes scientific consensus toward conclusions that months earlier would have seemed premature or reckless, but now appear inescapable, given systematic elimination of conventional alternatives. The mathematics of celestial mechanics display ruthless indifference to human curiosity as March of 2025 approaches. Proxima Centauri's position relative to Earth and Sun follows orbital paths determined billions of years ago, creating geometric alignment that will render PC-1 unobservable for 3 critical weeks, precisely when the signal may undergo its most significant transformations. The impending blackout represents not mere inconvenience, but fundamental barrier that no technological advancement can overcome. when target and sun occupy nearly identical positions in Earth's sky. The timeline unfolds with astronomical precision. By March 1st, Proxima Centauri's angular separation from the Sun decreases to 28 degrees as viewed from Earth, approaching the threshold where solar radio interference begins overwhelming faint cosmic signals. Professional radio observatories implement increasingly aggressive interference mitigation techniques, filtering solar noise that rises exponentially as separation angle shrinks. Each day sacrifices signal quality for continued observation as researchers struggle to extract data from degrading conditions. March 7th marks the effective end of practical observation when solar elongation drops below 20 degrees. At this geometry, scattered solar radio emission creates background noise levels thousands of times stronger than PC-1's received power. Even the most sensitive receivers cannot distinguish signal from solar interference when both sources appear so close together in the sky. The signal does not disappear suddenly, but fades gradually into overwhelming static, like whispers drowned by roaring wind, becoming progressively more difficult to detect until observation becomes impossible rather than merely challenging. The conjunction period extends through March 28th, encompassing 3 weeks when PC-1 remains effectively invisible from Earth-based facilities. This blackout occurs during what theoretical models predict should be critical evolutionary phase if signal intensification continues at rates observed through February. Maximum complexity, potential message content, or structural changes might all manifest during precisely the weeks when human telescopes cannot observe. The cosmic irony places revelation period behind solar interference barrier, as if universe deliberately arranged observation gap at most scientifically valuable moment. The physics behind superior conjunction involves no conspiracy against discovery, merely geometric consequences of observing from planet orbiting same star as target. As Proxima Centauri's apparent position approaches Sun's location in Earth's sky, angular separation decreases until the star appears to pass behind solar disk from terrestrial perspective. This creates observational conditions that no instrument design or signal processing technique can overcome when source and interference occupy overlapping sky regions. Space-based assets offer limited alternatives to ground observations, but face their own constraints. The Parker Solar Probe operates in inner solar system, where it theoretically might detect PC-1 from different geometric perspective. But the spacecraft's instruments focus on solar wind and coronal studies, rather than sensitive radio astronomy. Its receivers lack the bandwidth and sensitivity required for detecting narrow band signals at 1.42 gigahertz. The James Webb Space Telescope operates at infrared wavelengths, not radio frequencies, making it blind to PC-1 regardless of geometric advantages. Theoretical modeling attempts to predict signal evolution during the unobserved conjunction period based on trends established through February observations. If intensification continues linearly, PC-1 might reach detectability thresholds for amateur equipment by late March. If modulation complexity increases proportionally with signal strength, information bandwidth could expand to tens of megabits per second. However, the signal might also plateau, diminish, or cease entirely. During conjunction with no witnesses to document the transition, the forced observational hiatus creates unprecedented challenges for scientific community accustomed to continuous monitoring capabilities when studying variable phenomena. Modern astronomy relies on uninterrupted observation sequences, tracking objects through complete activity cycles. Comets require extended monitoring to distinguish temporary outbursts from sustained behavioral changes. Variable stars need long baseline photometry, separating intrinsic variation from instrumental effects. The 3-week gap in PC-1 coverage eliminates possibility of comprehensive analysis, just when such analysis becomes most crucial for understanding signal nature and intent. When observations resume in early April, Proxima Centauri will emerge from behind Sun into dawn sky, requiring reacquisition and recalibration after weeks of blindness. The signal that greets returning observers may bear little resemblance to transmission last detected in early March, potentially showing evidence of dramatic evolution that occurred hidden from view, or revealing unchanged persistence, suggesting automated beacon operation, indifferent to Earth's observational capabilities. The vigil ends on March the 29th, 2025, when Proxima Centauri emerges from behind the Sun's overwhelming glare into the pre-dawn sky. Radio telescopes worldwide turn toward coordinates that 3 weeks earlier held humanity's most compelling evidence for extraterrestrial technology. Uncertain whether they will detect familiar mathematical patterns, evolved transmission, or silence marking the end of the most extraordinary month in the history of astronomy. What observers find defies every prediction and transforms PC-1 from intriguing anomaly into undeniable confirmation that something unprecedented operates at our nearest stellar neighbor. The signal returns dramatically stronger than when conjunction forced observations to cease in early March. Received power measurements register at negative 118 decibels, 7 decibels above pre-conjunction levels. This represents a 5-fold increase in signal strength that cannot result from improved observational geometry or reduced solar interference. The source itself has intensified, either through increased transmitter power, tighter beam focusing, or both. Multiple independent facilities confirm the enhancement within hours of first detection, eliminating calibration errors or instrumental artifacts as explanations. More startling than raw intensity are the structural changes apparent in detailed analysis. The original single carrier wave at 1.42 gigahertz now appears accompanied by 15 additional frequency components spanning nearly 100 megahertz of spectrum. These new carriers maintain exact harmonic relationships with the fundamental frequency, positioned at precise integer multiples that create a frequency cone pattern familiar from optical physics, but unprecedented at radio wavelengths over interstellar distances. Each frequency component carries independent modulation, suggesting parallel information channels operating simultaneously. The mathematical encoding evolves from elegant simplicity to baroque complexity. Prime number sequences remain present as foundation, but now appear nested within higher order structures. Fibonacci progressions emerge in the spacing between pulses. Fractal patterns repeat at multiple timescales. The golden ratio appears not just in amplitude variations, but encoded in phase relationships between frequency components. The information density approaches theoretical limits for the available bandwidth, suggesting optimization for maximum data transmission within physical constraints. Dr. Amanda Chen's team at Caltech makes the breakthrough discovery on April 2nd while analyzing correlations between frequency channels. The 15 carrier waves encode what appears to be a two-dimensional array when their modulation patterns combine correctly. Rendering this array as grayscale image produces the first recognizable structure, a circular pattern divided into concentric rings with radial divisions, creating a coordinate system reminiscent of polar graphs used in mathematics and navigation. The image quality remains poor with only 64 by 64 pixel resolution, but the geometric regularity unmistakably represents intentional design rather than random noise. The timing correlation that sparked controversy in February returns with impossible precision. The signal transformation began approximately 4 hours after radio telescopes transmitted coordinated response toward Proxima Centauri on March the 24th, during the final days of conjunction, when most Earth-based facilities could not observe, but a few Southern Hemisphere telescopes maintained marginal detection capability. The 4-hour delay again violates light speed constraints that should impose 8-year round-trip communication time across the 4 light-year separation between civilizations. Multiple research teams independently verify the timing coincidence, calculating probability of chance correlation at less than 1 in 10,000. The pattern suggests either faster than light communication unknown to physics, prescient programming that anticipated human response timing with uncanny accuracy, or systematic observational bias, creating false correlation from coincidental events. None of these explanations satisfies scientific comfort, while all challenge fundamental assumptions about causality, intelligence, or methodology. The transformation forces recalibration of Rio scale assessment. What began as Rio 7 detection candidate now approaches Rio 8 or 9, representing high confidence technosignature with profound implications for human civilization. The structured image embedded in multi-channel transmission eliminates remaining doubt about information content. Something at Proxima Centauri deliberately encodes data into radio transmissions, using techniques that demonstrate technological sophistication and possibly responsive behavior to Earth-based signals. The post-conjunction signal shows no indication of diminishing or reverting to simpler structure. If anything, complexity continues increasing as daily observations through early April reveal additional layers of encoding and new frequency components appearing in the transmission. Whatever process initiated this evolution appears to be accelerating rather than stabilizing, suggesting either programmed sequence designed to gradually increase sophistication, or active adjustment responding to detection and characterization by human receivers. The detection of intelligent signals from Proxima Centauri forces humanity to confront a question that remained comfortably theoretical for 6 decades. Should we respond, and if so, who decides what message to send and under whose authority? By early April of 2025, the transformed nature of PC-1 eliminates any remaining doubt about its artificial origin, making the response question urgent rather than academic. The debate reveals deep divisions about risk assessment, governance legitimacy, and humanity's right to speak for Earth when the stakes involve potential contact with unknown intelligence. The ethical framework known as METI, Messaging to Extraterrestrial Intelligence, has generated controversy within the SETI community since its formalization in the early 2000s. Critics argue that advertising Earth's presence to unknown civilizations poses existential risk comparable to ancient islanders lighting signal fires visible to potentially hostile seafaring empires. Proponents counter that any civilization capable of detecting our response already knows we exist through decades of radio and television leakage, making intentional silence futile. PC-1's apparent responsiveness to human transmissions adds urgency to debates that previously remained theoretical exercises. The International Academy of Astronautics established guidelines recommending that no response be transmitted to confirmed detection without international consultation and consensus. However, these guidelines carry no legal authority, and no enforcement mechanism prevents individuals or organizations from broadcasting messages regardless of consensus. Multiple groups announce intentions to respond independently, creating coordination nightmare as competing visions of appropriate messaging threaten to flood Proxima Centauri with contradictory transmissions. The governance vacuum becomes apparent when the United Nations Committee on Peaceful Uses of Outer Space attempts to establish response protocols during emergency sessions in mid-April. 89 member nations hold widely divergent views about appropriate action. Some advocate immediate enthusiastic response, welcoming contact and offering friendship. Others demand complete radio silence until comprehensive risk assessment concludes. Still, others propose limited mathematical acknowledgement without substantive information about Earth's location, biology, or civilization. No consensus emerges after weeks of debate, leaving the question unresolved as private actors proceed with their own plans. Military and intelligence establishments view the response question through national security lens, fundamentally different from scientific or philosophical frameworks. Multiple governments classify their assessment of PC-1's implications, restricting information flow and conducting independent analysis outside public scrutiny. Defense agencies examine whether transmission technology capable of interstellar communication might indicate capabilities posing security threats. The possibility that advanced civilization exists at our nearest stellar neighbor generates classified strategic assessments, exploring scenarios ranging from benign contact to existential danger. Unauthorized transmission attempts complicate official coordination efforts. On April 9th, a private METI organization in California broadcasts a response message toward Proxima Centauri using leased time on commercial satellite uplink facility. The transmission includes mathematical primer, basic information about Earth's solar system, and stylized representations of human biology. News of this unauthorized broadcast generates immediate controversy and calls for regulation of transmissions directed toward confirmed intelligence sources. But legal frameworks for such regulation remain non-existent. The dark forest hypothesis enters mainstream discussion for the first time outside academic philosophy. This concept, popularized in science fiction, proposes that the universe resembles a dark forest where civilizations remain silent to avoid detection by potentially hostile neighbors. Under this framework, broadcasting responses to detected signals represents dangerous naivety that might trigger unwelcome attention from predatory intelligences. Critics dismiss dark forest thinking as paranoid speculation, but the hypothesis gains traction among policymakers responsible for considering worst-case scenarios. Religious communities respond with interpretations spanning from enthusiastic welcome of cosmic neighbors to theological crisis, questioning humanity's unique status in creation. Major religious leaders issue statements, ranging from the Vatican's measured acknowledgement that contact would not contradict Catholic theology to evangelical declarations that PC-1 represents demonic deception, The diversity of religious responses mirrors secular society's fractured reaction, with no consensus emerging about spiritual implications or appropriate action. Scientific organizations, including the SETI Institute and International Astronomical Union, attempt to coordinate measured response representing broad consensus, but the effort founders on fundamental disagreements about message content and transmission timing. Some researchers advocate immediate acknowledgement signal containing minimal information, essentially confirming detection without revealing substantive details. Others argue for extended silence, while humanity develops coherent strategy for contact, rather than rushing into communication with inadequate preparation. The response dilemma exposes humanity's inability to speak with unified voice or coordinate action on species-level decisions, with civilization-scale implications. Multiple contradictory responses likely already travel toward Proxima Centauri at light speed, carrying messages that may confuse, enlighten, or alarm whatever intelligence awaits them across 4 years of electromagnetic propagation through the interstellar void. The transformation of Proxima Centauri, Signal 1, from March through April of 2025, reveals technological capabilities that force reassessment of what advanced civilization might achieve. The 15-channel frequency comb transmission, embedded image data, and apparent signal processing sophistication demonstrate engineering approaches fundamentally different from human radio technology. Analysis of these capabilities provides indirect window into alien innovation, while simultaneously raising questions about applications and implications for Earth's own technological development. The frequency stability observed in PC-1 exceeds best human atomic clocks by 2 orders of magnitude. Maintaining 1.42 gigahertz carrier wave with drift below 0.001 hertz over weeks of observation requires oscillator quality factors approaching 10 billion. Current human technology achieves quality factors near 100 million in laboratory conditions, representing 100-fold gap between terrestrial and apparent Proxima capabilities. This precision suggests either exotic physics unknown to human science, or refinement of conventional techniques through centuries of incremental improvement beyond Earth's current development stage. Energy generation methods implied by signal strength calculations indicate civilization harnessing power at planetary scale. 5 megawatt continuous transmission assumes omnidirectional broadcast, but even optimistic beaming scenarios require hundreds of kilowatts sustained indefinitely. For comparison, Earth's entire radio astronomy infrastructure consumes equivalent power operating all facilities simultaneously. A society capable of dedicating such resources to single communication project either possesses energy abundance far exceeding human civilization, or prioritizes interstellar messaging above competing resource demands in ways suggesting fundamentally different economic or social organization. Information encoding efficiency approaches theoretical limits defined by Shannon's information theory. The bandwidth available between 1.3 and 1.5 gigahertz could theoretically carry maximum of approximately 200 megabits per second, given signal to noise ratios observed in PC-1 reception. Current modulation encodes roughly 50 megabits per second, representing 25% of theoretical maximum. Human communication systems rarely exceed 10% efficiency due to error correction overhead and practical implementation constraints. The high efficiency suggests either superior error correction algorithms or transmission environment cleaner than Earth's electromagnetically noisy civilization creates. The embedded image, encoding, reveals sophisticated data compression, achieving recognizable graphics in minimal bandwidth. 64 by 64 pixel image, transmitted as part of larger data stream, represents only 4,000 bits of information, yet conveys geometric structure clearly interpretable as coordinate system or navigation aid. Human image compression techniques like JPEG require substantially more data for comparable visual information, suggesting either different approaches to representing visual information or transmission of highly optimized symbolic representations rather than literal pictures. Patent and intellectual property questions arise as researchers analyze transmission techniques potentially applicable to human technology. Can methods extracted from alien signals receive intellectual property protection? Who owns rights to technologies reverse engineered from extraterrestrial sources? International patent law contains no provisions for non-human inventors or information sources originating beyond Earth. Legal scholars debate whether PC-1's mathematical encoding constitutes prior art invalidating future patent claims, or whether human implementations of alien techniques qualify as novel inventions deserving protection. Commercial space industry responds with mixture of excitement and concern. Companies developing satellite communication systems examine whether PC-1's frequency comb approach might improve bandwidth efficiency for terrestrial applications. Venture capital flows towards startups proposing to commercialize techniques inspired by analysis of the Proxima transmission. Simultaneously, aerospace corporations worry that revelation of vastly superior alien technology might devalue ongoing research investments if human approaches prove obsolete compared to extraterrestrial methods. Defense applications receive classified analysis separate from public scientific investigation. Signal processing techniques, encryption methods potentially embedded in modulation patterns, and transmission power management all carry dual-use implications for military communication systems. Intelligence agencies examine whether PC-1 reveals vulnerabilities in human radio infrastructure, or suggests novel approaches to secure communication that might provide strategic advantage. The technological gap implied by PC-1's characteristics forces uncomfortable questions about Earth's position in any broader galactic technological hierarchy. If Proxima civilization represents average or typical development level, humanity may occupy very junior position among spacefaring intelligences. Alternatively, PC-1 might represent unusually advanced society, and most civilizations cluster closer to human capabilities. Without additional data points, extrapolating from single example risks drawing conclusions from unrepresentative sample. The revelation that intelligence exists at our nearest stellar neighbor operating technology beyond current human capabilities creates complex emotional and strategic responses. Wonder at the achievement mixes with concern about implications. The universe has demonstrated that humanity neither stands alone nor leads in technological development. How we respond to that knowledge may determine our species' trajectory for centuries to come. The confirmation of intelligent transmission from Proxima Centauri triggers psychological and cultural responses that ripple through human civilization, with velocity rivaling the radio waves crossing space between stars. By mid-April of 2025, the reality of PC-1's artificial origin penetrates public consciousness despite official attempts at gradual information release. Humanity confronts the most profound shift in self-understanding since Copernicus displaced Earth from the center of the cosmos, discovering that we occupy a universe where intelligence exists beyond our planetary boundaries. Religious communities display remarkable diversity in theological responses to confirmed extraterrestrial intelligence. The Vatican releases a carefully worded statement acknowledging that Catholic doctrine never precluded the existence of other rational beings in God's creation, framing contact as expansion of divine plan rather than theological crisis. Islamic scholars debate whether Quranic references to creation of multiple worlds anticipate discovery of alien civilizations, or require reinterpretation in light of new evidence. Hindu and Buddhist traditions incorporate the revelation more easily, having long maintained cosmologies accommodating multiple inhabited worlds. However, fundamentalist movements within various faiths experience genuine crisis as literal interpretations of creation. Narratives confront empirical evidence of non-human intelligence. Some religious leaders declare PC-1 represents demonic deception designed to undermine faith, while others embrace the discovery as confirmation of divine creative abundance. The theological spectrum ranges from complete rejection to enthusiastic acceptance, mirroring the diversity already present in religious responses to evolutionary biology and cosmology. The psychological impact operates on both individual and collective levels. Surveys conducted during late April reveal that approximately 30% of respondents report feeling profound loneliness diminish upon learning humanity shares the universe with other minds. Another 25% express anxiety about implications and potential threats from superior civilization. The remaining population displays reactions ranging from indifference to excitement, with demographic patterns showing younger generations generally more comfortable with the revelation than older cohorts. Cultural production responds with remarkable speed as artists, writers, and filmmakers incorporate PC-1 into creative works. Science fiction authors who spent careers imagining first contact find reality surpassing fiction in unexpected ways. The discovery inspires musical compositions, visual art installations, and performance pieces exploring themes of cosmic connection and human identity in broader universal context. Popular culture begins processing the implications through creative expression faster than academic philosophy or sociology can formalize analytical frameworks. Educational systems face immediate pressure to update curricula reflecting new reality. Should schools teach about PC-1 in science classes, social studies, or both? How should educators address student questions about alien intentions and potential future contact? Teachers report increased student engagement with astronomy and physics as young people recognize these subjects now connect directly to the most significant development of their lifetimes, rather than remaining abstract academic exercises. The Fermi paradox receives practical resolution through single data point. The apparent silence of the cosmos troubled physicists for decades, with numerous proposed solutions ranging from rare Earth hypothesis to great filter scenarios, suggesting civilizations typically self-destruct before achieving interstellar communication. PC-1 demonstrates that at least some intelligences survive technological adolescence and maintain the capability and inclination for long-term transmission projects. The discovery shifts probability calculations about galactic civilization prevalence. Though single example prevents definitive statistical conclusions. Great filter theory generates renewed concern among futurists and existential risk researchers. If technological civilizations commonly exist but rarely expand beyond their home systems, some barrier might prevent interstellar colonization. PC-1's existence at our nearest stellar neighbor, yet apparent lack of physical presence in our solar system, suggests that either interstellar travel remains prohibitively difficult, even for advanced societies or civilizations choose not to expand physically, despite possessing communication technology. Both possibilities carry implications for humanity's own future prospects. Philosophical debates intensify around questions of cosmic purpose and human significance. Does intelligence at Proxima Centauri imply universe conducive to consciousness and mind, suggesting teleological dimension to physical laws? Or does PC-1 simply represent statistical inevitability in sufficiently large cosmos where improbable events become certain given enough opportunities? The discovery provides no definitive answers, but reframes questions humans have pondered since first contemplating stars. The social cohesion effects prove complex and contradictory. Some communities experience renewed sense of human unity when confronted with cosmic context, making terrestrial divisions seem petty. Others intensify existing conflicts as groups compete to define appropriate civilizational response to contact. International cooperation improves in some domains, while nationalist movements argue for preserving distinct cultural identities against potential homogenization in broader galactic community. The spectrum of explanations proposed for Proxima Centauri Signal 1 ranges from conservative natural phenomena to exotic possibilities that challenge fundamental physics. By late April of 2025, the transformed signal's characteristics have eliminated most conventional astrophysical mechanisms, yet scientific rigor demands examining the full range of hypotheses from mundane to extraordinary, before accepting conclusions that would reshape human understanding of our cosmic context. The conservative position maintains that PC-1 represents advanced natural phenomenon currently beyond our theoretical understanding. Proponents argue that claiming artificial origin based on failure to explain through known physics commits logical fallacy of argument from ignorance. Nature consistently produces phenomena more complex than human models predict, from ball lightning to fast radio bursts. Perhaps Proxima B's magnetosphere generates coherent radio emission through plasma processes involving exotic chemistry in its atmosphere. The mathematical patterns might emerge from resonance effects or harmonic relationships in physical systems, rather than deliberate encoding. This hypothesis preserves existing physics while acknowledging knowledge gaps, though it struggles to account for apparent responsiveness and image encoding. The automated beacon scenario offers middle ground between natural and actively intelligent explanations. This hypothesis proposes that PC-1 originates from ancient automated system constructed by civilization that may no longer exist. The beacon operates according to programmed instructions, broadcasting continuously or periodically for millennia without conscious oversight. This explains technological sophistication while avoiding questions about current alien intentions or capabilities. The signal's evolution might reflect pre-programmed sequences designed to gradually increase complexity rather than responsive adaptation to Earth's transmissions. However, this scenario cannot easily explain timing correlations between human actions and signal changes, unless invoking remarkably prescient programming. The active communication hypothesis suggests living civilization deliberately attempting contact with Earth or conducting systematic survey of nearby star systems. Under this framework, PC-1 represents intentional message crafted specifically for detection and interpretation by technological societies. The mathematical structure serves as universal language announcing intelligence, while embedded data conveys substantive information about senders' knowledge, capabilities, or intentions. The signal evolution demonstrates responsive behavior as Proxima civilization detects Earth's acknowledgement transmissions and adjusts their message accordingly. This explanation accounts for all observed characteristics, but requires accepting that intelligence exists at our nearest stellar neighbor and possesses both capability and motivation for interstellar communication. Speculative hypotheses venture into territory where current physics provides limited guidance. Some researchers propose that PC-1 might employ faster than light communication through mechanisms unknown to standard model particle physics. Quantum entanglement, wormhole networks, or tachyon transmission could theoretically enable near instantaneous information transfer across interstellar distances, explaining apparent 4-hour response times. However, these mechanisms remain purely theoretical, with no experimental evidence supporting their feasibility for macroscopic communication. The probe scenario suggests PC-1 originates not from Proxima system itself, but from automated spacecraft studying our solar system from Proxima vicinity or preparing closer approach. This hypothesis explains signal characteristics while allowing that transmitter operates in interstellar space rather than orbiting Proxima b. Advanced civilization might deploy self-replicating probes throughout galaxy, with one unit positioned near Proxima Centauri, detecting Earth's technological development and initiating contact protocols. The scenario remains speculative, but internally consistent with observations. Exotic possibilities include simulation, hypothesis, implications, where PC-1 represents communication from whatever entities operate the simulated reality we inhabit. Under this framework, the signal need not originate from physical location at all, but rather injects information into simulated universe through mechanism appearing as radio transmission from Proxima Centauri. This unfalsifiable hypothesis generates philosophical discussion, but offers no testable predictions, distinguishing it from conventional explanations. Temporal paradox scenarios propose signal might originate from Earth's own future, transmitted backward through time, using physics beyond current understanding. The mathematical structure could represent messages from humanity's descendants attempting to influence their own past. This explains apparent foreknowledge of human responses, while requiring acceptance of closed time-like curves and violations of causality that most physicists consider impossible. The critical perspective emphasizes that extraordinary claims demand extraordinary evidence, regardless of how poorly conventional explanations fit observations. History demonstrates that apparent mysteries often receive mundane explanations once sufficient data accumulates and theoretical frameworks mature. PC-1 may eventually yield to natural explanation. Through physics, humanity has not yet discovered rather than requiring artificial origin. Scientific humility demands acknowledging limits of current knowledge while maintaining standards of evidence, before accepting civilization-altering conclusions. The transformation of Proxima Centauri Signal 1 accelerates through late April of 2025 as the transmission transitions from elegant mathematical announcement into torrent of structured data that overwhelms analysis capabilities of facilities designed for passive listening rather than active decoding. On April the 23rd, PC-1 undergoes dramatic shift that multiplies information bandwidth by factor of 10, flooding receivers with complex modulation patterns that require immediate expansion of data, storage infrastructure, and processing capacity beyond anything astronomical community anticipated. The bandwidth expansion occurs over approximately 6 hours as additional frequency components activate across spectrum between 1.2 and 1.6 gigahertz. By the transition's completion, observers detect 47 distinct carrier frequencies, each independently modulated with sophisticated encoding schemes. The aggregate information rate reaches approximately 500 megabits per second, equivalent to streaming high-definition video. Radio telescope data pipelines designed to handle kilobits per second from typical astronomical sources face immediate saturation as terabytes of time series measurements accumulate faster than analysis teams can process. Storage infrastructure proves inadequate within 48 hours of transition. The Very Large Array's primary data storage fills completely by April the 25th, forcing emergency procurement of additional disk arrays and implementation of real-time compression algorithms to manage incoming flow. FAST in China experiences similar crisis, implementing aggressive data thinning that discards fine temporal resolution to preserve spectral information. Coordinating what data to keep versus discard becomes a critical decision with potential consequences for missing crucial information embedded in discarded portions. Pattern recognition systems achieve breakthrough on April the 27th, when machine learning algorithms trained on the expanded data stream identify repeating structural elements suggesting modular information encoding. Dr. James Rodriguez's team at Stanford discovers that the 47 frequency channels organize into 7 groups containing similar modulation patterns, potentially representing parallel transmission of related content through redundant channels for error correction. This redundancy implies sender anticipates noisy reception conditions and designs transmission to remain decodable despite significant information loss. The image hypothesis gains dramatic confirmation when researchers successfully reconstruct higher resolution graphics from the expanded data. Where earlier transmissions yielded 64 by 64 pixel images, the April data produces recognizable visuals at 512 by 512 resolution. The first clear reconstruction shows what appears to be a diagram of planetary system, with central star and multiple orbital paths marked with symbols that might represent mathematical quantities or physical parameters. The image quality remains primitive by human standards, but represents enormous improvement over earlier fragmentary reconstructions. False start discoveries plague analysis efforts as teams announce interpretations, later proven incorrect by additional data or alternative processing approaches. On April 29th, European researchers claim to identify linguistic structure in modulation patterns, proposing that PC-1 encodes alien language. Within 24 hours, competing analysis demonstrates the supposed linguistic patterns result from processing artifacts rather than genuine signal characteristics. The incident highlights dangers of premature conclusions when analyzing unprecedented data under intense public and professional pressure for results. Coordination between research groups becomes essential as data volume exceeds any single facility's processing capacity. International collaboration emerges where teams specialize in different aspects of the transmission, with some focusing on image reconstruction, others examining mathematical structures, and still others searching for physical constants or scientific information encoded in the data stream. This distributed analysis approach proves more effective than individual efforts, but requires careful protocols for sharing intermediate results and validating conclusions across independent groups. The signal termination prediction adds urgency that sometimes compromises analytical rigor. Multiple theoretical models suggest PC-1's high bandwidth phase cannot continue indefinitely, with estimates for transmission cessation ranging from early May to mid-June. Researchers race to extract maximum information before potential signal end, creating pressure to publish findings rapidly rather than pursuing exhaustive verification. The tension between speed and accuracy generates heated debates about appropriate standards when analyzing data that may never recur. Commercial entities propose crowdsourcing analysis by distributing data to volunteer computing networks similar to projects like SETI at home. While this dramatically expands processing capacity, it raises concerns about data security, premature public disclosure of unverified findings, and coordination challenges managing thousands of independent analysts applying inconsistent methodologies. The convergence of multiple detection methods transforms Proxima Centauri Signal 1 from isolated radio anomaly into component of broader evidence pattern, suggesting technological civilization operates in that system. Throughout early May of 2025, researchers correlating PC-1 characteristics with atmospheric observations of Proxima b discover relationships that elevate confidence in artificial origin hypothesis, while simultaneously raising profound questions about what intelligence might exist on that distant world. The James Webb Space Telescope's infrared spectroscopy of Proxima b's atmosphere, conducted during multiple observation sessions between March and May, reveals chemical signatures that resist easy natural explanation. Water vapor appears in concentrations suggesting liquid surface water, while methane and oxygen coexist in ratios indicating active replenishment against photochemical destruction. Most intriguing are trace absorption features, potentially matching industrial fluorocarbons, synthetic chemicals never observed in planetary atmospheres, lacking technological civilizations. Dr. Sarah Kim's team at NASA Goddard Space Flight Center performs detailed correlation analysis between atmospheric composition measurements and PC-1 transmission timing. They discover that signal intensity variations correlate weakly, but significantly, with Proxima b's orbital phase, suggesting connection between atmospheric conditions and transmission characteristics. During periods when spectroscopy indicates enhanced atmospheric activity on the planet's day side, signal strength increases by approximately 2 decibels. This correlation supports hypothesis that transmission originates from or passes through Proxima b's atmosphere rather than operating in empty space. The oxygen-methane disequilibrium chemistry observed in Proxima b's atmosphere has generated debate since initial detection in 2024. These gases react rapidly to form carbon dioxide and water, requiring continuous replenishment to maintain observed concentrations. Biological processes offer one explanation: as photosynthetic organisms produce oxygen, while methanogenic bacteria generate methane. However, the specific concentration ratios differ from Earth's biosphere, suggesting either different biochemistry or significant industrial contribution to atmospheric composition. Technosignature researchers propose that PC-1 represents intentional supplement to atmospheric biosignatures, a deliberate communication strategy where civilization advertises presence through both biological markers, detectable via spectroscopy, and technological signals, detectable via radio astronomy. This dual approach ensures detection by observers using either method, dramatically increasing probability of contact. The hypothesis gains support from timing analysis showing PC-1 activation correlates with period when Earth's improving telescope capabilities made Proxima B's atmospheric characterization feasible. The synthetic chemical detection remains controversial, with significant uncertainty in spectroscopic interpretation. The absorption features attributed to fluorocarbons appear near detection limits and might result from instrumental artifacts or misidentification of natural molecular species. Multiple research groups analyze identical data and reach contradictory conclusions, with some claiming definitive detection and others arguing. The signals remain ambiguous. The debate highlights challenges of characterizing exoplanet atmospheres, where faint signals must be extracted from overwhelming stellar contamination. Comparison with Earth's own atmospheric evolution provides context for interpreting Proxima B's chemistry. Human industrial activity altered Earth's atmospheric composition measurably within decades of industrialization, introducing pollutants detectable by hypothetical alien observers. If Proxima civilization follows a similar technological trajectory, their atmosphere might preserve chemical fingerprints of industrial development, alongside biological signatures from native ecosystems. The concentration levels observed suggest either early industrial phase or civilization practicing atmospheric management to control pollution. The convergence of radio technosignature and atmospheric anomaly represents multiple independent lines of evidence pointing toward same conclusion, dramatically strengthening the case for intelligence at Proxima Centauri. Statistical analysis calculates that probability of both PC-1 and atmospheric chemistry arising from natural processes drops below 1 in 1 million when evaluated jointly rather than separately, while neither detection alone proves artificial origin beyond doubt. Their combination creates evidential framework far more compelling than either observation individually. However, the correlation also enables alternative interpretation, where both phenomena share natural explanation. Perhaps Proxima b experiences unusual geological activity, driving both enhanced radio emission through mechanisms not yet understood, and atmospheric chemistry through volcanic outgassing with exotic composition. This unified natural explanation preserves conventional physics while accounting for multiple observations, though it requires invoking coincidences and unknown processes that some researchers find equally implausible as accepting extraterrestrial technology. The unprecedented nature of Proxima Centauri. Signal 1 forces scientific methodology to adapt under conditions never anticipated when empirical frameworks were developed through centuries of terrestrial research. By mid-May of 2025, the astronomical community grapples with fundamental epistemological challenges. How does science proceed when studying unrepeatable phenomenon, when experimental controls prove impossible, and when the subject of investigation potentially possesses intelligence comparable to or exceeding human capabilities. The reproducibility crisis that plagues many scientific fields reaches extreme form with PC-1 analysis. Traditional science demands that experimental results be independently verified through repeated trials under controlled conditions. Yet PC-1 represents a singular event occurring 4 light-years away under conditions completely beyond human control or manipulation. No researcher can repeat the observation from the beginning, adjust variables, or conduct controlled experiments. The signal either continues or ceases according to processes at Proxima Centauri entirely independent of terrestrial scientific requirements. Peer review processes strain under the volume and urgency of PC-1 related research. Journals receive hundreds of manuscript submissions analyzing various aspects of the transmission, overwhelming editorial capacity for thorough evaluation. Preprint servers become primary venue for rapid information sharing, with researchers posting analyses within days of completing them, rather than waiting months for traditional publication. This acceleration enables faster scientific progress, but increases risk of uncorrected errors propagating through literature before thorough vetting identifies problems. The verification challenge becomes apparent when multiple research groups analyze identical data and reach contradictory conclusions. A claimed detection of visual information in the signal by one team fails reproduction when others apply different processing algorithms to the same raw observations. Are the differences due to legitimate interpretive disagreement, or does one group make methodological errors? Without ground truth to adjudicate disputes, consensus emerges slowly through weight of evidence rather than definitive proof. Statistical rigor proves difficult to maintain when sample size equals 1. How confident should researchers be in conclusions drawn from single instance of interstellar signal? Traditional hypothesis testing assumes multiple trials, allowing calculation of probabilities and confidence intervals. PC-1 permits no such luxury. Astronomers apply statistical methods designed for large datasets to analyze one transmission, raising questions about whether conclusions meet conventional significance thresholds, or whether extraordinary circumstances justify relaxed standards. The observer effect takes potentially literal form if PC-1 demonstrates responsive behavior to human transmissions. In quantum mechanics, observation affects measured systems. With PC-1, human actions might genuinely influence the phenomenon under study if intelligence at Proxima Centauri detects and responds to Earth's broadcasts. This creates methodological nightmare, where attempting to study the signal potentially alters its characteristics, violating fundamental scientific assumption that observation should not disturb the system being measured. Falsifiability, the criterion philosopher Karl Popper proposed as distinguishing science from pseudoscience, becomes complicated in contact scenarios. What observations would definitively falsify hypothesis that PC-1 represents extraterrestrial technology? Signal cessation might indicate natural transient phenomenon, or could simply mean the transmission ended according to alien schedule. Lack of semantic content might suggest natural source or reflect communication difficulties. Nearly any observation permits multiple interpretations, making definitive falsification extraordinarily difficult. The balance between caution and urgency generates tension throughout the research community. Conservative scientists advocate withholding conclusions until evidence becomes overwhelming and alternative explanations are exhaustively eliminated. This rigorous approach minimizes false positive risk, but potentially delays recognition of genuine discovery. Progressives argue that accumulating evidence already exceeds reasonable doubt thresholds, and that excessive caution prevents society from preparing for implications of confirmed contact. Interdisciplinary collaboration becomes essential as PC-1 analysis requires expertise spanning radio astronomy, signal processing, information theory, linguistics, cognitive science, and exobiology. However, different disciplines employ different methodological standards and evidentiary requirements. What constitutes proof varies between fields, creating friction when researchers from diverse backgrounds attempt to reach consensus about interpretation and implications. The new epistemology emerging from PC-1 analysis may influence how science approaches other singular extraordinary phenomena. The methodological adaptations developed for studying interstellar signals could apply to other unrepeatable events, like hypothetical detection of dark matter particles, observation of primordial black holes, or characterization of other exoplanetary technosignatures. PC-1 serves as test case for how empirical investigation proceeds when traditional experimental controls become impossible, yet phenomena remain scientifically tractable through careful observation and analysis. The breakthrough arrives not through human insight, but through pattern recognition algorithms operating beyond conscious analytical capabilities. On May 12, 2025, a neural network trained on mathematical texts identifies recursive structure embedded within Proxima Centauri Signal 1's modulation that human researchers overlooked for weeks despite intensive analysis. The discovery opens floodgates to semantic interpretation that transforms PC-1 from mysterious transmission into comprehensible message, containing verifiable mathematical proofs, and what appears to be invitation encoded in universal language of geometry and physics. Dr. Elena Vasquez's team at MIT deploys machine learning system originally designed for theorem proving in abstract mathematics, training it to search for logical relationships within PC-1's data stream. The algorithm identifies sequences where earlier transmitted patterns serve as axioms from which later patterns follow through valid logical inference. The structure mirrors mathematical proof methodology, where each statement builds upon previous established results. By May 14th, the system extracts complete proof of theorem from number theory, demonstrating that sum of two odd primes can express every even integer greater than 2, a conjecture human mathematicians call Goldbach's hypothesis and have pursued unsuccessfully for centuries. The verification process confirms the proof's validity through independent checking by multiple mathematics departments worldwide. The logical steps withstand rigorous scrutiny, representing genuine mathematical discovery regardless of origin. This achievement demonstrates PC-1 contains not merely patterns suggesting intelligence, but actual knowledge demonstrating capabilities exceeding current human mathematics in at least some domains. The implications prove profound. Intelligence at Proxima Centauri possesses mathematical understanding sufficient to solve problems that eluded Earth's finest minds. The embedded primer hypothesis receives dramatic confirmation as researchers identify teaching sequence within the transmission. Early portions establish basic mathematical operations. Through examples and repetition, Middle sections introduce geometric concepts and coordinate systems. Later transmissions build progressively complex ideas, culminating in physics equations describing orbital mechanics, electromagnetic radiation, and quantum phenomena. The structure suggests deliberate pedagogical design intended to establish shared conceptual framework before conveying complex information. Coordinate data emerges from geometric sections of the transmission. Multiple research groups independently extract what appears to be three-dimensional spatial information, encoded as angles and distances. When plotted, the coordinates describe structure matching known geometry of Proxima Centauri system, including stellar position, planetary orbits, and potentially artificial objects or facilities. One particularly intriguing coordinate set appears to indicate location approximately 0.1 astronomical units from Proxima b, possibly identifying transmission source position. Temporal information embedded alongside spatial coordinates suggests timing component to the message. Researchers identify counting sequences, potentially representing calendar or scheduling information. One interpretation proposes the numbers indicate duration in Earth days until significant event, though what that event might be remains subject to intense speculation. The countdown, if correctly interpreted, reaches 0 in mid-June of 2025, approximately 1 month following the breakthrough discovery. The invitation hypothesis gains support from analysis of final sections in the current transmission sequence. Symbolic representations combining spatial coordinates, temporal markers, and repeated mathematical emphasis on specific orbital configurations might constitute meeting proposal or observation window notification. Some researchers interpret the data as suggesting optimal time and geometric alignment for enhanced communication or possibly physical rendezvous, though this latter interpretation generates controversy given enormous distances and travel time requirements. Semantic content extraction reveals that perhaps 20% of transmitted data now yields to interpretation using the mathematical and geometric frameworks established through the primer sections. The remaining 80% contains structures not yet understood, either awaiting additional context for interpretation or employing encoding schemes beyond current analytical capabilities. Each successful decoding enables interpretation of additional previously opaque sections as researchers build cumulative understanding of communication protocols. The breakthrough generates immediate public and governmental response as news spreads that PC-1 contains actual comprehensible information rather than mere mathematical announcement. Media coverage intensifies dramatically. Government agencies demand access to decoded content for security review. Religious leaders request information about theological implications. The astronomical community faces unprecedented pressure to accelerate interpretation while maintaining scientific rigor in claims about message meaning. Controversy erupts over interpretation uncertainty, with skeptics arguing that humans impose meaning on ambiguous data through pattern matching rather than extracting genuine alien intent. The debate mirrors historical arguments about interpretation of ancient texts or archaeological artifacts, where multiple readings remain possible and definitive truth proves elusive. However, mathematical proof validity provides objective verification that at least some interpreted content represents genuine transmitted knowledge rather than observer projection. The astronomical community watches the calendar with growing tension as predictions indicate Proxima Centauri Signal 1 will cease transmission during the first week of June 2025. Multiple theoretical models analyzing bandwidth evolution, power consumption trends, and embedded temporal markers converge on estimates placing signal termination between June 1st and June 7th. The countdown to Transform's final observation, weeks into urgent race to extract maximum information before losing access to the most significant astronomical phenomenon in human history. The prediction basis rests on pattern analysis, revealing systematic progression in PC-1's characteristics since re-emergence after March conjunction. Signal complexity increases following predictable curve that mathematical modeling suggests cannot continue indefinitely without exceeding physical constraints on information density and transmission power. The temporal markers decoded in mid-May explicitly encode duration counts that reach 0 on June 1st by most interpretations, strongly suggesting planned termination date rather than indefinite transmission. Final observation windows generate unprecedented coordination as facilities worldwide organize continuous coverage, ensuring no gaps in monitoring during critical period. Southern Hemisphere observatories coordinate with northern stations to maintain 24-hour surveillance as Earth's rotation carries individual telescopes in and out of view of Proxima Centauri. Amateur astronomers contribute to distributed monitoring network, providing redundancy against equipment failures at professional facilities and democratizing participation in historic moment. Equipment failures plague observations with frustrating regularity as Murphy's Law asserts itself during worst possible timing. The Effelsberg telescope in Germany experiences receiver failure on May 23rd, requiring 3 days of emergency repairs that eliminate crucial European coverage. FAST in China faces cooling system malfunction on May 27th that reduces sensitivity by half until technicians restore full functionality. Each outage creates gaps in data record that may contain irreplaceable information transmitted once and never repeated. The psychological pressure intensifies as researchers work 18-hour days attempting to decode remaining signal content before access terminates. Sleep deprivation and exhaustion lead to errors that waste precious time pursuing false leads. Team leaders struggle to maintain morale and analytical rigor while acknowledging that opportunity slips away hour by hour, regardless of human effort or dedication. The emotional toll manifests in stress-related illness, interpersonal conflicts, and occasional breakdown, requiring temporary reassignment of personnel. Media frenzy reaches fever pitch as June approaches, and news outlets worldwide cover the impending signal termination. Networks broadcast countdown clocks, creating sense of global anticipation, mixed with anxiety about what cessation might mean. Does termination indicate message completion with successful communication established? Or does it represent failure where transmission ends before humanity adequately comprehends content? Public expectation management becomes impossible as speculation outpaces factual information. The final decoded sections contain what appears to be valediction or closing statement, though interpretation remains contested. Some researchers identify symbolic representations suggesting completion and satisfaction with communication exchange. Others interpret identical data as expressing regret about limitations or indicating future communication attempts under different conditions. The ambiguity frustrates efforts to prepare appropriate human response before contact window potentially closes. Contingency planning addresses scenarios ranging from signal continuation beyond predicted termination to complete cessation followed by permanent silence. International committees debate whether humanity should transmit final acknowledgement message before June 1st or await signal behavior before responding. The coordination challenges that plagued earlier response efforts persist, with multiple groups preparing independent transmissions, reflecting divergent views about appropriate content and tone. Amateur astronomers equipped with modest equipment report detecting PC-1 as signal strength continues increasing through late May, confirming predictions that intensification would eventually enable backyard observation. This accessibility transforms professional scientific phenomenon into public experience as thousands of individuals worldwide personally verify transmission existence through their own receivers. The distributed observation network provides resilience against any single point failure, while creating data management challenges as observations flood in from uncalibrated sources. The countdown creates historical parallel to other moments when humanity collectively awaited transformative events, from solar eclipse expeditions testing general relativity to Apollo missions landing on the Moon. However, PC-1 termination differs through its alien agency, where outcome depends entirely on decisions made 4 light-years away by intelligence, whose motivations and capabilities remain fundamentally uncertain despite weeks of intensive study. The termination of Proxima Centauri Signal 1 on June 1st, 2025 marks not an ending, but a transformation in how humanity monitors our nearest stellar neighbour and prepares for potential signal recurrence or evolution. Within hours of transmission cessation, international astronomical organisations convene emergency planning sessions, establishing comprehensive long-term observational strategy, spanning decades and incorporating next-generation technologies, not yet deployed, but anticipated within coming years. Continuous monitoring becomes permanent priority, with major radio observatories worldwide allocating dedicated observation time to Proxima Centauri, regardless of signal detection. The Very Large Array commits 10% of annual schedule to systematic surveys of the 1.2 to 1.6 gigahertz band targeting Proxima system. FAST in China implements automated monitoring protocols, checking for signal re-emergence during every visibility window. This sustained vigilance ensures humanity will detect any resumed transmission within hours, rather than weeks or months of its appearance. The Square Kilometre Array project receives dramatic funding increase as governments recognise strategic importance of expanded radio astronomy capabilities. SKA construction timeline accelerates with first phase elements becoming operational in the late 2020s, providing sensitivity improvements of 2 orders of magnitude over existing facilities. This enhanced capability will detect signals far weaker than PC-1 or resolve fine structure invisible to current instruments, potentially revealing communication activity at Proxima Centauri operating below previous detection thresholds. Next-generation Very Large Array planning incorporates lessons from PC-1 observations. The NGVLA design emphasizes wide instantaneous bandwidth to capture complex multi-frequency transmissions and includes dedicated high-speed data processing infrastructure, preventing storage bottlenecks that plagued April observations. Projected completion in the mid-2030s will provide capabilities specifically optimized for technosignature detection and characterization based directly on experience analyzing the Proxima transmission. Interstellar probe mission concepts receive renewed attention and funding as space agencies worldwide recognize that 4.2 light-years represents achievable, if challenging, distance for robotic exploration. Breakthrough Starshot Initiative, proposing laser-propelled light sails capable of reaching Proxima Centauri in 20 years, gains political support and investment previously unattainable. While actual launch remains years away, pending technology development, the mission planning transitions from speculative proposal to serious engineering project with defined timeline and budget. 20-year roadmap anticipates potential signal recurrence around 2045 if PC-1 operates on cyclic schedule with 2-decade period. 50-year planning addresses scenarios where response to Earth's transmissions arrives after 8-year round-trip light travel time. Century-scale strategy contemplates possibility that meaningful exchange requires patience measured in human lifetimes as civilizations separated by interstellar distances conduct conversation at glacial pace imposed by physics. Funding influx transforms SETI research from perpetually underfunded niche field into strategic scientific priority, commanding resources comparable to particle physics or space exploration programs. National science foundations worldwide establish dedicated techno-signature research programs. Private philanthropy supplements. Government investment as billionaires recognize historic significance of potential contact and direct wealth toward detection infrastructure and analysis capabilities. Political capital for space science reaches levels not seen since Apollo era as public fascination with PC-1 creates constituency supporting ambitious astronomical projects. Politicians who champion expanded radio telescope networks and interstellar probe development gain electoral advantages, fundamentally altering cost-benefit calculations that previously constrained such initiatives. The sustained public interest generates virtuous cycle where successful observations justify continued investment, enabling more capable future detection systems. The Proxima Centauri Signal 1 detection serves as mirror reflecting humanity back to itself, revealing capabilities and limitations that remained theoretical until tested by genuine contact scenario. The 5-month experience from January through June of 2025 exposes how human civilization responds under pressure of potentially civilization-altering discovery, providing lessons about cooperation, decision-making, and collective psychology that extend far beyond radio astronomy. Global cooperation achieves unprecedented success in some domains while failing dramatically in others. The Coordinated Observation Campaign demonstrates that humanity can organize effective international response when faced with shared challenge requiring technical expertise and resource pooling. Radio observatories on 6 continents share data seamlessly, establishing protocols for real-time collaboration that previously existed only on paper. However, response coordination collapses into competing national and organizational interests. When questions shift from observation to action, revealing persistent barriers to unified decision-making on species-level questions. Technological capabilities prove simultaneously more advanced and more limited than pre-contact assessments suggested. Humanity possesses sufficient radio astronomy infrastructure to detect and characterize interstellar signals when they appear, validating decades of SETI investment despite earlier skepticism. Data processing and machine learning tools enable extraction of meaningful information from unprecedented transmissions. Yet storage infrastructure, bandwidth capacity, and analytical frameworks require emergency expansion to handle data volumes that planning documents never anticipated, exposing gaps between theoretical readiness and practical implementation. Societal resilience demonstrates remarkable stability as billions of people process confirmation that intelligence exists beyond Earth without experiencing predicted social collapse or widespread panic. Religious institutions adapt theological frameworks. Educational systems incorporate new knowledge. Popular culture processes implications through creative expression. The apocalyptic scenarios imagined in contact literature prove unfounded as humanity absorbs paradigm shift with surprising equanimity, suggesting greater psychological flexibility than pessimistic projections assumed. The contact experience reveals evolutionary implications as humanity confronts confirmed existence of intelligence, potentially millions of years more advanced. Natural selection operating on cosmic timescales might favor civilizations that survive self-destructive technological adolescence and develop capabilities for interstellar communication. PC-1 demonstrates that such survival remains possible, providing existence proof that great filter barriers can be overcome and technological societies can achieve longevity sufficient for sustained transmission projects spanning potentially thousands of years. Individual psychological responses range across spectrum from profound existential comfort at learning humanity shares universe with other minds to anxiety about implications of superior civilization existing at our doorstep. Survey data reveals age correlates with comfort levels. Younger generations raised with exoplanet discoveries and astrobiology research integrate the revelation more easily than older cohorts for whom alien intelligence remained science fiction rather than scientific possibility. The detection forces confrontation with human limitations, including inability to achieve consensus on response strategy, tendency toward anthropomorphic projection when interpreting alien signals, and persistent tribal divisions that prevent unified action even when facing cosmic context that renders terrestrial conflicts trivial. These limitations prove neither shameful nor surprising, but simply accurate assessment of species evolved for small group cooperation, facing challenges operating at civilization scales. PC-1 teaches that humanity stands ready for contact in technical capabilities, while remaining unprepared in governance structures and decision frameworks. The gap between astronomical readiness and institutional preparedness shapes ongoing efforts to develop protocols, legal frameworks, and international agreements that might prove adequate should future detections occur, or should PC-1 resume transmission requiring coordinated response. The lessons learned during 2025 inform preparation for contact scenarios that may unfold across coming decades as humanity transitions from isolation to awareness of cosmic community. The detection of Proxima Centauri Signal 1 reshapes scientific priorities and cultural consciousness for generations following its June 2025 termination. The 5-month transmission leaves legacy extending far beyond accumulated terabytes of data, fundamentally altering how humanity perceives its cosmic context and directing research trajectories across multiple disciplines for decades into the future. Educational impact manifests immediately as students worldwide cite PC-1 as inspiration for pursuing careers in astronomy, physics, engineering, and related fields. University enrollment in STEM programs increases 20% in academic year following the detection. An entire generation grows up knowing with certainty that intelligence exists beyond Earth, fundamentally shaping their worldview and career aspirations in ways that will influence human civilization's direction through the remainder of the 21st century. Economic transformation concentrates in space. Industry sectors as commercial entities recognize strategic and financial opportunities in technologies related to interstellar communication and eventual travel. Investment in radio astronomy equipment. Manufacturing increases fivefold. Companies developing advanced propulsion systems for interstellar probes attract venture capital previously unavailable. The economic ecosystem surrounding space technology expands dramatically as PC-1 demonstrates both scientific importance and potential commercial applications of capabilities required for detecting and interpreting extraterrestrial signals. Geopolitical rebalancing occurs as nations compete to lead in technologies relevant to interstellar communication and space exploration. Countries with advanced radio astronomy programs gain prestige and influence. International partnerships form around shared interest in contact research, creating diplomatic connections that transcend traditional alliance structures. The space race paradigm re-emerges not as competition for lunar or planetary exploration, but as effort to achieve technological capabilities, enabling meaningful participation in potential ongoing dialogue with Proxima Centauri civilization. Cultural evolution toward cosmic perspective accelerates as humanity integrates awareness of confirmed alien intelligence into collective consciousness. Philosophical frameworks emphasizing Earth's uniqueness or human centrality lose credibility. Educational curricula incorporate astrobiology and comparative civilization studies. Popular culture increasingly features realistic, rather, than fantastical portrayals of alien contact based on lessons from PC-1 experience. The psychological shift from cosmic isolation to awareness of galactic community proceeds gradually across generations, but proves irreversible. Pending questions and mysteries multiply despite 5 months of intensive analysis. Why did transmission terminate on predicted schedule? What triggered initial activation in late 2024? Does cessation indicate message completion or represent pause before resumed transmission? Will Proxima civilization detect and respond to Earth's acknowledgement messages? The unanswered questions drive continued research and observation, ensuring sustained funding and attention for radio SETI programs. The detection establishes empirical foundation for previously speculative fields, including xenolinguistics, comparative cognitive science examining non-human intelligence, and techno-signature theory, analyzing how advanced civilizations might advertise their presence. These disciplines transition from theoretical exercises to practical research areas with real data from genuine extraterrestrial source. Academic departments emerge dedicated to studying implications and conducting follow-up research on PC-1's decoded content. Long-term societal effects remain uncertain as humanity processes implications across timescales spanning decades or centuries. The knowledge that intelligence exists 4 light-years away influences everything from religious belief to resource allocation priorities to philosophical frameworks about consciousness and purpose. Whether this knowledge ultimately proves beneficial or detrimental depends on how humanity chooses to respond, what lessons we extract from the experience, and whether we develop wisdom proportionate to our technical capabilities for detecting and potentially communicating with cosmic neighbors. The legacy of Proxima Centauri Signal 1 ensures that future generations will remember 2025 as year humanity definitively learned we are not alone, transforming from isolated civilization into aware participant in whatever broader cosmic community exists among the stars. The signal goes silent at 0347 Universal Time on June 1st, 2025, exactly as temporal markers predicted. Radio telescopes monitoring Proxima Centauri detect the final modulated pulse at 1.42 gigahertz, followed by return to baseline noise levels, indistinguishable from empty interstellar space. The most compelling evidence for extraterrestrial intelligence in human history ceases as abruptly as it began, leaving astronomers worldwide staring at flat spectral displays where complex mathematical patterns transmitted for 5 months now show nothing but cosmic static. Immediate verification confirms the termination occurred simultaneously across all observing facilities within light travel time differences, eliminating local interference or equipment failure as explanations. The source truly stopped broadcasting. Analysis teams scramble to extract final information from terminal transmission segments, discovering what appears to be closing sequence, encoding summary of primary message content, along with symbolic representations. Some interpret as farewell, while others read as promise of future contact. The question that dominates discussion in hours following silence asks whether humanity correctly interpreted the message. 5 months of intensive analysis decoded perhaps 30% of transmitted content, extracting mathematical proofs, coordinate data, and structural information about Proxima's system. The remaining 70% resists interpretation despite application of every analytical technique available. Did the transmission succeed in its communication goals? Or does the silence represent failure where humanity proved inadequate receivers, unable to comprehend intended message? Monitoring continues unabated as observatories worldwide maintain constant surveillance of Proxima Centauri despite signal absence. The vigil operates on multiple timescales, addressing different recurrence scenarios. Hourly monitoring detects immediate resumption if transmission restarts on short cycle. Daily observations track potential signals operating on rotation or orbital periods. Monthly surveys search for seasonal variations or longer-term patterns. This layered approach ensures detection regardless of recurrence timing, while efficiently allocating limited telescope resources. Humanity's response message completes transmission toward Proxima Centauri on June 15th, following weeks of international debate, producing consensus text. The message acknowledges PC-1 detection, confirms successful interpretation of mathematical content, expresses gratitude for communication attempt, and requests clarification of undecoded portions. The transmission employs frequency and modulation schemes, matching those used in received signal, maximizing probability of recognition by whatever systems monitor for responses. Now begins the wait measured in years as radio waves cross 4.2 light-years of void. 3 possibilities frame uncertainty about what the silence means and what might follow. The transmission could represent message from civilization that no longer exists, automated system continuing to broadcast long after its creators disappeared through war, environmental catastrophe, or evolutionary transformation. Alternatively, Proxima intelligence might remain active but dormant regarding Earth contact, having transmitted their message and now awaiting human response across the 8-year round-trip light travel time. Third possibility suggests active observation, where Proxima civilization monitors Earth's reaction to their signal, perhaps evaluating humanity's technological and social development before proceeding to next communication phase. The cosmic conversation has begun, regardless of which scenario proves accurate. Humanity transmitted acknowledgement that will arrive at Proxima Centauri in 2029. Any response to that message will reach Earth in 2033, 8 years after PC-1 first appeared in our receivers. This conversation proceeds at pace dictated by physics rather than human impatience, measured in presidential terms rather than news cycles, unfolding across timescales that test civilization's capacity for sustained attention and multi-generational commitment. The vigil represents more than astronomical observation. It embodies humanity's transition from cosmic isolation into awareness and tentative participation in whatever broader community exists among intelligences scattered through the galaxy. We watch, we listen, we wait, and in waiting, we demonstrate patience and persistence that may themselves constitute communication across the light years.